this one. Okay, this one. Seria E. 1, 2, 1, 2, C-E-A-C-O-A. Okay, so here we have this microphone. I think it's E-E-E-A-C.
Yes.
Probably on that stand. I don't know if you want to have the microphone here with you or on the stand.
Is there another microphone, only this one? Or?
We just have one handheld and
That one, only
that
two.
one on the.
Okay, I thought
on the
there.
right side.
Okay, because maybe this room is a little bit slower. I think yesterday we got in the other room, right? So we have lots of microphones. Okay, never mind.
Okay, but this one is here on the first. I will label this. Okay.
Yeah.
This one.
Ok, aqui eles estão a falar. Exactly. Eles mudaram alguma coisa? Pois, até a posição aqui disto está um bocadinho diferente. Está mais longe. Ok. Provavelmente vão estar a essa distância e já vão estar a falar. Não necessariamente a esta altura. Até com um bocado. Pois estão a falar assim. 1, 2, 1, 2. Teste. 1, 2. Splash. Pois isto está um bocadinho diferente. Estou a falar, 1, 2, 1, 2, teste, estamos aqui a testar o som, 1, 2, A, B, B. Depois quando aproximo um bocado já começa a fazer feedback. Depois já mudaram isto.
Fala lá mais um bocadinho.
Sim, estou a falar, 1, 2, 1, 2, Splash, Huawei, Cascais, 2023, Video Prime Video na verdade, Google, IBM, Twig, Huawei, 1, 2, 1, 2. Estamos aqui, dia 22/10, às 10h20, não, às 10h37. Pois, estou a falar, 1, 2, 1, 2. Pois até a coluna, acho que essa daí do canto, eles mexeram um bocadinho. Não estava tão para o meio. Ou estava? Ok, ok. 1, 2, 1, 2. Teste, 1, 2. Os graves.
Yeah, it's.
If you go there, it's like.
Exactly.
But.
Yeah,
They probably will be standing here and talking from this far.
Okay. All right. Is it okay? Yeah, it's okay.
We'll manage it during when you start.
Yeah.
We'll be here. We'll manage it. The output to your stream and the sound in the room. We'll start to manage it.
Yep.
Okay, thank you.
But probably.
I should tell them to a little bit closer, maybe. Yeah, make a stick, make a speaker.
Where do people use their laptop?
Ah, it's in here. Exactly. There's here each HDMI cable.
So we don't have any adapters, right? Maybe for macOS.
I have one myself in my bag, so I'm lending to people who need it.
Okay. I want to get some water.
C, E, A, E, A, U, E, 1, 2, 1, 2, C, E, A.
Exactly. There's a cable there.
Already received the printed award.
I don't know who to ask.
Okay, I will go upstairs to the student
Yeah,
room to
that would be great.
Do you need them today or is it?
So I think for one of them we need it today.
Oh, okay.
For one of the most influential.
So
it'll be very
for the session in the afternoon.
yeah, in the
Okay,
afternoon.
yes,
Yeah,
okay,
yeah, yeah. But for the rest, tomorrow together with SLE.
Okay, you're on
Yeah.
top of those.
Yeah,
things,
yeah,
okay. I will just ask whether they have printed.
Yeah, thank you, thank you. Perfect. It's me.
Hi, I'm a volunteer for this one.
Yeah, sure.
Samir.
Yeah, nice to meet you. I'm me. Yeah.
So, I'm a student, I'm volunteer for the AV's part.
Mm-hmm.
And I'm a support volunteer.
Okay, so what's the difference?
I will
I think it means-
do something related to the
Okay, okay.
laptop.
So,
I will manage other things, I think.
oh, the mic.
Yeah,
just
there's the
start.
presentations before the presentation,
Yeah.
set up the microphone.
Okay.
Cool, cool, cool.
So I
Great,
think
great.
we shall stay together.
Yeah.
Yeah.
Yeah, I just asked them, they have printed the awards, but only one copy per paper. So they're going to add some more for the other authors. But in the end, we can get them.
Okay, so they will have it like
Yeah,
that.
yeah, normally yes.
Yeah, I was
But
wondering
it's a
whether I
little
should
bit
tell
on-
them. But
Yeah,
I felt that from the count of the others.
Yeah, but it's printed on very thin paper though.
Okay, that's all. Thanks.
There will be something.
Yeah.
So there, take a look. Okay, it works.
I'm Eric Heidi.
Nice to meet you. I mean,
I was hoping to do an AV.
yeah, sure, sure, sure. Do you want to try it here? Do you have USB-C? Yeah.
No, I have HDMI.
Oh,
But I also have,
Perfect.
I also have UBC, but I would just
Yeah,
use
okay.
HDMI.
okay. So let me.
No, I'm not, I'm the first paper, but I'm after the introductions. Yeah.
If you want to give it a test.
Yes. Is there a lavalier mic, or is this the only mic? Okay. So that means that I need to stay here. Because otherwise yeah, okay. Well, that's,
You have an handheld microphone, this is the
ah, so there's also a handheld mic.
Would you want one? Which one do you prefer?
Let's see. Well, probably, just one minute. This should be fine. Well, my remote doesn't seem to work. Maybe I'll move less than I thought I did, since my presentation remote doesn't seem to want to work. So, anyway, I think I'll be good. Thank you. I can do that. I wonder why my remote, I mean, the presentation is working fine. I was just trying to,
Do you want to move it closer to you so that it would be louder, the voice?
I will do that.
Okay.
I can do that.
Okay.
So, mhm. How interesting.
How about just make it show like my default screen instead of like popping up a desktop too?
Let me go check.
Yeah, things are fine. Just need to refocus a bit. Well, sorry. Yeah, because if I drag this manually, then
Yes.
I have
May
to.
I?
Yeah, yeah, please.
Okay, so
Resize
this
it.
is this one.
Oh,
And
second screen.
display. Where did you see that? No, it's the screen and where is it?
Or there's a screen something.
Display.
Oh, screen saver. Is it displays?
It is. This one is different from mine. Built-in display, no key,
Yeah, it keeps updating.
range, user main display, automatically.
Oh, so it's extending the display instead of
Yeah.
mirroring.
I think
Yeah,
we should choose mirror.
you should have a little
Wait, I
tick
tried
box.
just clicking on this, but it didn't show.
User main display, extend display.
Oh, there's a mirror.
Yeah,
Is
we
that
should
the
choose
one?
mirror.
So it's here. This is different from my Mac, so but
Okay,
I
so
think
if I,
I think this is the new Mac.
so if I click on presentation
the,
mode,
the,
and it works.
the software should be well.
Can it fit
could
like the
be.
whole screen? Not the black background
I
around it?
don't think so because even here
Exactly.
it's smaller.
Oh,
Okay.
that's interesting. It wasn't like that before. Huh, interesting.
So what's the aspect ratio for the screen here?
16 by 9.
16:9.
Yep. 16 by 9. So
Okay,
this one is
I guess we
4.3.
yeah, I can live with that.
Yeah, you needed to change the aspect ratio.
How do I do that? Is it somewhere like in the setting of the display or?
No, I think it's probably in
it's
the
the presentation.
I just enter the presentation mode. Like, is there something else I need to do?
Okay, can
Yeah, yeah, please go ahead.
view.
I think we have like 1 more minute.
No, this view is from.
It is a
from-
Firefox.
From
Oh.
other.
Well, I actually think
How
it's
do I
fine.
go to
10,
the
15,
menu?
18 already.
It's Max and I don't use it. I don't
It's
really know
okay,
how
it's okay.
does it
I
how
don't.
does it work.
Oh,
Let me help you.
it's fine. Yeah. No, I think it's fine.
Hello, everybody. Yeah, this is the first part of the first session, so it's the welcome session. And this is Amir Sheikha from the University of Edinburgh in Scotland, United Kingdom, together with Kun from VUB. I cannot pronounce the university name very well. I can pronounce Edinburgh now. Welcome to GPC 2023. So this year we decided to add two additional topics, AI and ML techniques for generating code and low-code, no-code approaches. And also we added an additional paper category, which we called it Generative Perl. And this was inspired by the functional Perl category from ICFP, and also the Perl category from ECOOP. And the basic idea is that if you have some line of work that is interesting from the kind of programming point of view, but you don't really see that much kind of research contribution inside it, you can target this paper category. So unfortunately this year we didn't have any submission there, but now that you know about it more, perhaps the next years you can try this category. And also for the first line, I don't think we have any accepted paper. We had some submissions, but unfortunately they didn't make it. So we had a very busy summer. Perhaps not the authors, but the reviewers and the program committee. So the submission deadline was July 14th, and then we asked them to actually, in a bit more than a month, to finalize the reviews so that we can publish them for the authors for 3 days author response. There were some reviews which were delayed, and we announced them a bit late, like by 1 hour, but we gave like 1 additional day for the authors to submit their responses. And then we had a very intensive PC discussion period, and for many of the papers I can say that the discussion already started before the authors provide a response. And then we sent out the notification on September 3rd. And so the entire review process was double-blind, and we had, of course, managed the conflict of interest. And this year we have made sure that all the papers get 4 reviews. There was one paper, only one paper that unfortunately just got 3 reviews. And then, as I said, we had a very intensive PC discussion period. So initially we managed to attract 27 abstract submissions, but 3 of them decided not to submit at the end of the day. And we had 24 paper submissions, and out of which the PC, the program committee decided to accept 11 papers. And for actually one of the papers, the consensus was that, okay, let's accept it as a short paper. And so in terms of the countries that submitted this year, again, Germany is leading. So I do have also the statistics from 2022. So in 2022, the UK was the second, and this year Japan is the second. I call it the PC chair effect. So basically the PC chair last year was from Japan, so now it's the second leading, but last year, so this year it's from the UK, so the UK was the second. So I hope that the next year UK is gonna again become the second and overtake Japan, perhaps. I don't think there is any chance to overtake Germany. And the third one is the Netherlands. So if you see the numbers, we have some sort of fractions. So if there was a paper with 3 authors, and one of them was from Netherlands, we would call it 0.333. And then Spain with 2 submissions, 2 full submissions, the USA, Switzerland. So there was one, the only single author paper was from Switzerland, who is going to present in this session. And there was another paper which had, I think, 3 authors, and 2 of them were from Switzerland. I forgot about the other one. And then, Sweden is the next, and then UK is actually part of the others now, which had only 1 paper, which is going to present in the session after this one. These are the statistics for the last year. You can see that how Japan has gone from the 6th place to the 2nd place now. And in terms of submissions by years, I think we are, it's kind of oscillating. Hopefully for the next year, we're going to attract more submissions. And in terms of the acceptance ratio, I think it's always in the range of, staying in the range of 50%. So this year it has been slightly lower than 50%. And the entire program was handled by many different people from all around the world. So you can see that there are 27 amazing researchers who have helped us with selecting the line of papers that are going to be presenting today. And let's thank all of them. I don't know. So because of the entire schedule for the SPLASH, it's really challenging to basically ask all of these reviewers to provide the reviews during their summer break. It has been really difficult, I can say. Difficult for them and also difficult for the organizers, because in some cases you have to chase the reviewers. This year, again, we have a 2-day semi-full lines of talks. So today, we are going to have 3 sessions. So the first session, which is right now, immediately after this welcome talk by me, there are going to be 2 paper presentations. And then immediately after the lunch break, there is going to be another session, which includes 3 paper presentations. And so last year, GPC didn't have the most influential paper from 2012. So this year, instead, we are going to have 2 most influential paper presentations from both 2012 and 2013. So tomorrow, we are going to have 2 long talks, basically. So I think this is the first time that GPC has a tutorial session also. So Jeremy Yalop kindly has accepted that invitation to give a tutorial on a new macro system for OCaml. And then it's going to be followed by a keynote from Julia Laval, which is going to be joined with the SLE. And immediately after the keynote, we are going to have an award session, which I'm going to tell what are the award winners next. And so the award session, again, is going to be joined with SLE. And after that, again, in the afternoon, we are going to have 2 sessions, which each of the sessions, again, is going to have 3 paper presentations. And yeah, that's about all the program. So yeah, let's talk about the most influential papers. So for GPC 2012, the steering committee actually decided to, based on the based on the impact that each of these papers had, decided to give the award to XSpace, implementing domain-specific languages for Java. So is any of the authors here right now? So there is going to be a session in the afternoon, as I said, for the most influential papers. And for GPC 2013, the award went to the paper, Does the Discipline of Preprocessor Annotations Matter? A Controlled Experiment. And is any of the authors for this paper here? No. Okay, I think in the afternoon we are going to meet them. And of course, as I said, there is going to be an award ceremony happening tomorrow, right after the keynote. And yeah, so the program committee has decided to give the best paper award of this year to the paper C to Taco, Lifting Tensor Code to Taco. So yeah, the first author of that paper is over there. So we are going to thank you tomorrow. But his talk is going to be immediately after lunch in the session in the afternoon, before the most influential paper sessions. And yeah, there is not that much else to say right now. So the proceedings have been made available. So I've created a QR code. If you want to scan it, you can go and download it. And yeah, that's it. I think I was a bit faster than expected.
So because we have an online,
Mm-hmm.
do you want me to come up now, or do you want me to wait 15 minutes?
I think we can wait 30 minutes just to be on plan.
You get to decide.
Yeah, I think we can wait. So we're going to start our research sessions. So the first actual speaker of today is Eric ID from the University of Utah. And he's going to talk about generating conforming programs with XSmith.
Thank you so much. Thank you, everyone, for coming to my talk. So this is a talk about random testing of programming language implementations, and we're aiming to find deep bugs. So let's start off by talking about those three things. So has everyone done random testing? It's a very popular thing. It's very fun. So random testing is a procedure like this, right? Up at the top, we have some kind of tool that generates a random input. That random input, we give it to a system that we're trying to test, and we see what that system does with it, right? If we decide if the output is correct, according to whatever test metric we have, then that's fine, and we go back and start generating more tests again. Otherwise, if the system under test didn't respond correctly, we've found a bug, and our testing has been valuable to us, right? So we're going to instantiate that in this talk, okay? Up at the top, we're going to have program generators built on this tool called XSmith, and in the middle, we're going to be testing the implementations of various programming languages, okay? So we're interested, imagine this sort of hypothetical pipeline for a traditional compiler or interpreter. We're interested in finding bugs that give us wrong answers, okay? That cause wrong answers to be produced by the programs that we're trying to execute, right? So we want to find bugs all the way at the end of this pipeline, okay? So what is it that we could generate to try and do these, right? Well, a lot of people using common tools like AFL++ or whatever, these things generate random byte sequences. And of course, random byte sequences, with few exceptions, are not source code programs. And so this thing doesn't get us very far towards finding our goal, right? Okay, so we can generate, of course, token sequences. This is a little bit better, gets us past the lexical analysis stage, but again, we're not getting very far in terms of our pipeline because it doesn't get past the parser. We can generate more grammatically correct inputs, right? But this doesn't get us very far because this code here has obvious type errors, and the compiler spits that out during its analysis. And we can generate statically correct programs, things that type check, things that are grammatically correct and syntactically correct. But here, we might have all kinds of behaviors when this program is executed that cause the program not to have a meaningful answer, right? So in this case, x is a small array, and function f might return some unknown result, and so we would get some sort of undefined behavior if we tried to execute this C code, which means that it's not going to be a very good test case for us in terms of deciding whether or not this program has a right answer or a wrong answer. Okay, so we actually need to generate not only all things that are correct along all this pipeline, but we need to generate programs that are also dynamically correct. Okay, so we need programs that conform strictly to the language specification for whatever language it is that we're generating. And this is where the word conforming comes from in the title of my talk. We're looking for programs that strictly conform to the language specification. Okay, we want programs, if it strictly conforms, it means that it's free from undefined and non-deterministic behaviors, which means that our programs have answers, and they're useful for us, right, to use as test cases for a programming language implementation. So creating a program generator like this is a lot of work. Okay, so some years ago, I was an implementer of a tool called CSmith, which is a generator of C programs, right? And this was published some time ago. And CSmith is 39,000 lines of code, and it consumed a PhD student and a couple of professors for a couple of years, right? And so if I really want to do this, so we did, I think, a good job doing this for C, but now we're interested in doing it for Java. We're interested in doing it for Racket. We're interested in doing it for Python. How long am I going to live? Not long enough to test all those languages, right? So let's try and make it easier, okay? So now I finally get to tell you about the last part, the interesting bit of this talk about XSmith. So XSmith is a tool for creating random program generators, right, of conforming programs for many programming language implementations. XSmith it implements a DSL for defining different sorts of aspects of a generator, okay? It comes with a library of parts that you can incorporate into a new program generator, okay? So you don't have to do all of the work yourself, okay? And in terms of evaluation, we've implemented several test case generators on top of XSmith, and we found that it supports program generators with small implementations. Ideally, these things that indicates that it's easier to write these specifications, right? And we've evaluated we've proven this technology through the discovery of many unknown defects in 4 programming language implementations, okay? So now let's get into talking about how XSmith works, okay? So at a high level, somebody who wants to use XSmith writes a program generator specification and feeds it to XSmith, okay? XSmith reads that specification, it processes it, and it produces a random program generator for the language that is described by the specification, okay? And these things, XSmith and the generator that it produces are implemented in a programming language called Racket. I don't know if you're familiar with Racket, but you can think of it as a modern dialect of Lisp, okay? The random program generator we then run, and we get a output program, which is a test case that we can use for random testing, okay? And of course, you can run it again and again and again to get a million test cases, okay? So what is it that you write in a specification? So here's the first thing that you typically would have to write for a language specification, some kind of grammar, something that's going to describe the syntax trees, the abstract syntax trees that we're going to produce. Okay, so this is a little excerpt for sort of a calculator kind of grammar. You can see sort of the standard BNF-like things, right? We have an expression node kind that is an abstract. We can't actually make just expressions, but we have add, which is a kind of expression. We have div, which is a kind of an expression, and we have int, which is also a kind of an expression, okay? Add and div have left-hand sides and right-hand sides, and integers have an attribute, which is the concrete value, okay? So this gives you a little bit of feel for this basic, the basic property, right? So let's talk about how XSmith uses this to generate abstract syntax trees, okay? So for this example, let's just assume that we've configured XSmith in a way I haven't told you, that is we want to generate a random tree that has a height of no higher than 2. Okay, so when XSmith starts off, it creates a special node, a whole node that represents the program that we're going to generate. Okay, and the hand is pointing to our current node. Okay, so now what we need to do is we need to fill the hole. So XSmith then goes off and it makes what's called a choice object, and it makes one for every node kind that could possibly fill that hole, right? So the top node type is an expression, so the things that could possibly fill here, it would be an add expression, a div, or an integer, okay? And these are objects that represent, so it makes this set of objects, and each one of these objects represents the possible choice of choosing that production, okay? There are a set of methods on each of these objects that tell XSmith whether or not that choice is going to be feasible in the current context. Okay, and these things can look at the current context. It can look at the attributes of the nodes that we're trying to fill. Okay, but pretty much this is sort of straightforward. So we've made the current choice objects. It turns out that all of these are feasible right now, and so we make a random choice, and we'll make, in this little example, we'll choose add. So we'll replace the whole with an add. Okay, and that add has that particular attribute has an attribute that says that it's a depth 0. So now we find the current hole and we go again, right? So here, all the current objects, we can pick add, div, or int again. Okay, we'll make a random choice this time. We choose div. Okay, so now we're down to this hole. We choose again. Okay, now it turns out, so now I've made these choice objects. Okay. And XSmith queries each one, runs the methods, and it says, oh, well, I can't do add or div, because if I made either one of those choices, I would have children, the holes that I would need to fill, and that would ultimately mean that my tree would be too tall. So these objects get disqualified, and of course then it chooses an integer. And you can imagine this is obviously a very simple example of how things work, but essentially you can, this is the general process by which we go about building up these trees. Okay, so nodes have attributes of various kinds, okay? And we have these choice classes, from which we make these choice objects that represent the possible choices that we can make. XSmith wraps these things up together in what we call a property. And a property is essentially sort of a mini DSL within XSmith that describes some aspect of the language. And XSmith provides you with a variety of different built-in properties, and the author of a generator can make their own property. Okay? So here is an example of, again, a pretty simple property. Okay? So just like we were making random choices before, this is sort of an aspect of that says, well, let's weight those choices a little bit, right? So we'll make divide nodes twice as popular as integer nodes, assuming that they're both feasible, okay? So here's another property, and this gets at a different aspect. This is the standard property for rendering nodes, okay, which we call render node info. And again, down at the bottom, right, we have the properties defined for add, div, and int, right? And each one of those essentially is a function that's going to tell XSmith what it needs to do in order to render this. And this is a pretty simple example. It's just going to render it in sort of this infix notation. But this is the sort of thing that an XSmith author would have to write in order to turn the generated AST into a string or something else that can ultimately be output and given to the system under test. Okay. So types are encoded as properties. We have a standard property called type info, okay, which allows you to define the type framework for your language, at least to the extent that it matters for generating random programs. Okay. The framework allows you to define some base types, right? So if you're doing some sort of C or WebAssembly-like language, and you have an I32 type, there are common type constructors for functions and products and structures and things like that, right? And because this is a property, right, it works with attributes, and it has an influence on the choices that XSmith will make when it builds up the tree, right? So type unification, as we consider what nodes are possible where in the tree, right, these type rules can get invoked, and we can say, can we put a node of this type at this position in the tree? That's a question that's answered by how someone fills in their type info property, right? So now I'm going to show you an excerpt from a WebAssembly generator, right? So we're going to have three simple nodes here. We're going to have literal integers, right? We're going to have variable defs and variable gets. And the value that's going to be associated with each of these node kinds, we have to associate two values with each of these. We have to say that if XSmith chooses this node, what are the types that a node of that kind can possibly inhabit? Okay? And then we have to have a function that says, if I choose this node, what are the type constraints on this node's children as a function of the type of the node itself, okay? And that's given as a dictionary or a map, right? So fleshing this out a little bit, take a look at the int32 one. Int32 is simply an I32. It is exactly the base type, okay? And you can look, a literal integer has no child types, right? And if you look down at the bottom, it says, yeah, this is an empty map. I have no map, no constraints on any children, right? So a variable def is a fresh number, and if you look down at the bottom, I would be pointing, but I'm not pointing because I'm on TV, right? Is that, so fresh number is a type variable. It says it has to be some kind of number, and these essentially are all the primitive types inside of WebAssembly, okay? And it says whatever the initializer of this is, a node of this type T, its initializer also has to be of that type, okay? So, pretty straightforward. You use this framework to specify the rules of your language, right? So now I want to move on to the canned components, right? So the abstract grammars of many programming languages are quite similar. They have similar statements, they have similar expressions, they have similar loop constructs. And we say, well, we can generate a lot of that by, for free. We can make it easy for people to just add all of this complexity to their the specification for their new language, and just have it go, right? So we try to reduce the effort through providing people with a standard library of these components, and so there's some, add basic statements, and you can say which ones you want to do. So for JavaScript, you might add blocks and return statements and if then else's, right? There's also an add basic expressions and add loop over container, right? So how did we evaluate XSmith? We evaluated XSmith in two particular ways, right? The first is our goal was to make it easier for people to create new random program generators, again, towards the goal of creating program generators that are useful for finding deep bugs, which means that we have to generate conforming programs, things that are dynamically correct. Okay. The second way, of course, is we look to see whether or not we actually found any deep bugs with the program generators that we created. So here's a comparison. So down up at the top of this, right, is the line counts for 3 conforming program generators from previous literature for generating C and Verilog and SQL. Okay. Down at the bottom is a set of random program generators that we created using XSmith, right? And in general, you'll see that, not surprisingly perhaps, right, our DSL seems to be effective. We're using the canned components, and their implementations are not teeny. They're not, in general, trivial, but they are much smaller, which gives us some hope that in fact, it is easier to implement these kinds of program generators using XSmith. And I just want to mention the bottom 3, Python, Lua, and JavaScript. These have not been used in substantial fuzzing campaigns. But, as I said, they have significantly smaller implementations. They generate conforming programs, right, which is a difficult constraint. And also they generate featureful programs, meaning that they exercise a lot of the low programming language features. So then we looked at the bugs, right? So this table shows crash bugs, semantic bugs, and static non-crash bugs. Crash bugs, right? You get the thing to crash, and this doesn't necessarily require a conforming program. The second one, however, right? These are bugs. We put bugs in this category when it corresponds to the program producing an incorrect result when it's executed. Okay, and about half of the bugs that we found fall into this category, right? And static and non-crash bugs are bugs that are sort of similar, failure to compile a correct program, other sorts of similar bugs like that don't necessarily require a conforming program, but still are near the back end of the implementation pipeline, right? And that's also about half, right? So altogether, these are the deep bugs that we were looking for, and almost all of the bugs that we found using the XSmith generators that we created are, in fact, the kinds of bugs that we were looking for, okay? So Racket, here's you always got to see some bugs, right? So the test case that I'm showing you here is the reduced version of a much larger test case that was produced by our Racket program generator, okay? And this was a bug that was in Racket 7.9, which at the time, so Racket 7.9 had 2 different back-end implementations, right? And basically, in one of these implementations, GCD was returning a negative number, although its specification says that it has to return a positive number, right? And Matthew Flatt, who is one of the primary implementers of Racket, said that this bug was, in fact, more than 20 years old, okay? So, one win. We found a bug using our Daphne program generator. So Daphne is a proving system, okay? And this particular bug was found through verification testing. We produced programs that have print statements, okay? And then what we do is so we would observe the output that is from the print, okay, which is the output of a Daphne backend. It can be compiled to Java or C# or other kinds of things. And then we replace the print with an assertion, which is evaluated by the verifier, which is earlier in the chain. And then we look to see whether or not the assertion matches the output of the print. Okay? And this is a way of sort of self-validating Daphne. And here's a bug, right? Where it says, yeah, it turns out that here, the printed output doesn't agree if you try and make the assertion earlier on, and that's just a miscompilation in the back end, right, where superset was being miscompiled as subset, right? Okay. So a WebAssembly bug. right? So this is in an implementation of WebAssembly called WASMer. It has two backends called CraneLift and LLVM, right? And in the LLVM implementation, if you try and figure out what this is doing, it's rotating a constant by 0, right, which should be an identity, but in fact, one of the backends returns -1 for this program, right? And the developer commented and said, this is a great bug, so that made us feel good. So anyway, conclusions. So XSmith is our tool for creating random generators of conforming programs. It is primarily a DSL for writing these kinds of specifications, but it also includes a substantial library for these components. And through our evaluation, we've shown that our goal was to reduce the effort required to create these kinds of program generators, right? And we have some evidence from the program generators that we've created that their implementations are, in fact, much smaller, right? And we could create them more quickly than we created CSmith, so I guess that's additional sort of anecdotal evidence that I will share with you, right? And, our goal was to find deep bugs in implementations of many different programming languages, and we sort of validated that by finding 46 deep bugs in 4 different programming language implementations. So, if this is exciting to you, you can, if you've got Racket on your computer, you can type this, Rako package install XSmith right now, and you can download it and install it and try it out. So, thank you very much. I'd be happy to take questions. I guess we have a microphone for people who want to ask questions, and since I can't see the online, I don't know if anybody's asking online, but.
Greetings for online people as well. One very little question just to make sure that I understand, and one deeper bug question. The first one, did you try to re-implement CSmith in XSmith?
No, we did not. So we did implement a C program generator.
Right.
But obviously, we did not really carry that all the way forward to the point where it has all of CSmith's features.
Right. So it sort of works, but you did not push for the level of maturity of CSmith.
That's
for
right.
obvious reasons.
That's right.
Okay, good. And the second one is about the canned components. So I'm sure once you start talking about semantics and boxing things, then a lot of people will remember funcons, for instance, or some other.
I'm sorry, what?
Funcons, functional components of Peter Moses and CBS and this kind of modular semantics.
Mm-hmm.
So have you looked at those, or how do you position this with respect to those? And in general, how sure are you about this?
Yeah, so this is a great question. So I'm not familiar with the exact piece of work that you're familiar with. I am familiar with Redx. I don't know if you're familiar with Redx. This is a semantics tool that's implemented in Racket. And in general, right, so there are these tools that work with semantics as sort of formal objects, right? And you can look for different kinds of consistency or these kinds of properties, right? Our goal here, right, is not really to specify semantics. Our goal is to test the implementations, right? And in general, most of our, deciding whether or not the output of a randomly generated test case is right or wrong. So you could do that with appeal to the semantics, but in fact, that's not generally what we do, because we find the semantics hard to work with, and in case there's, we still don't know if the implementation, is fully implementing the semantics. What we tend to use is differential testing, actually. So, anyway, but that's a great question, and sort of the nutshell answer is that we're really out to test implementations, right, rather than dealing with the semantics, and that just it changes the kind of tool that you build. Yes.
Hi, thank you for the very, very interesting presentation. I was wondering, when you mentioned the assertions and how you checked correctness, I would like to know how this work relates to, say, property testing tools like QuickCheck and this whole family of random generation of test cases, because I feel there's a similarity.
There is a similarity. So that's often referred to as property-based testing, right? And the kind of differential testing of entire programming language implementations is a kind of property-based testing, right? We're coming up with with random inputs, and we have, right? So with property-based testing, you often have also again, you have a specification of what the answer is supposed to be. Here, we often don't know what the answer is going to be, and again, and so how do we know whether or not the answer is right or wrong? Again, we generally rely on differential testing. Now here, of course, we have a different, for Daphne, the particular thing that you were talking about. Again, the goal here was not necessarily, when I say verification testing, as was framed in Daphne, doesn't require us to know exactly what the answer is, right? What we're looking to see is whether or not the answer that we get from the verifier is the same as the answer that we get from the compiled version of the program, right? So we're checking for consistency between two different parts of Daphne, right? So, but anyway, excellent question. Yeah, was there another question? Yeah.
Yeah, thank you for a very interesting talk. Maybe you say something about this, but so for integers, you could choose just a random value, but for identifiers or references, you have to actually choose something that exists already. How can you deal with this?
Yeah, so I didn't talk about that in this talk for time. We have a system for keeping track of definitions and keeping track of the scopes in which they're available, and then we have tools that allow you to make a random choice of a location that is in scope that meets the type requirements that you have, right? So, and you can do this, say, for choosing a random function. You know, you've generated a whole bunch of functions and you want to call one, but you have some constraint on the output type that you're expecting, right? You need something that returns an integer or something like that, right? So you can choose from the set of functions that return integers, right? Excellent question, though. Yes?
Yeah, really interesting talk, thank you. I was curious, I thought I saw maybe that JavaScript had like 42 lines or 400 lines of
Yeah, let me pull that up.
So my question is sort of in the lines of the coverage of the semantics, right? That if you think you're going to generate programs in the language, you could get away by, you know, not doing anything for a certain type in a language, a certain construct in a language,
Right.
and not generate those, but still have a great tool for like finding bugs for the parts you consider.
Right.
To what extent can you cover like the space of all valid language, of all valid programs in a language? Is it a matter of just like writing more and more of a specification, or so my questions are on
Yeah,
coverage,
these are actually very sophisticated questions, and I don't have enough time to give them full justice, I think. So the first thing I want to mention is that this particular JavaScript, you know, we do not cover all of JavaScript in 412 lines, right? This was sort of a proof of concept, and like I said, we didn't use this in a major fuzzing campaign, okay? So that said, right, so how do you know if you're covering all of the semantics? You can't just from XSmith itself, because XSmith doesn't know what the semantics are, right? But again, our job is, the way that we look at it is that, again, we're not trying to build a tool for covering the semantics. XSmith, right, is, let me say this differently. Not every user of XSmith wants to create a tool that covers the entire semantics of the system under test. They're interested in testing particular parts of that semantics as implemented by a particular implementation. So often a developer says, oh, I know that floating point in my language is screwed up, right? So I want to make test cases that do a lot of stuff with floating point, and I do not care about strings. I do not care about structures, right? So I'm going to make myself a test case generator that covers this subset of the language, and I'm going to ignore the rest of it, right? So if you cover all of the productions in your language, right, it is conceivably possible that XSmith could generate any program in this way, right? But it does require tuning in terms of which random choices you make and how often and how big your programs are. And the last thing I want to say is that your question brings to mind a paper that appeared at PLDI this year that I had nothing to do with, okay, but that was very interesting in terms of creating test cases from a formalized JavaScript specification, right? and they were trying to do coverage of various kinds over this formalized semantics. And so if you're particularly interested in an answer to that, I suggest that you look, and of course I can't credit the authors here because I've forgotten who the authors are, but I do remember the work. Oh, you do?
No, I will go look.
Oh, okay, yeah.
Thanks very much.
Yeah,
I'll catch you
okay.
later for more talk.
Thank you. Is that it?
Yeah.
All right, thank you very much.
Let's thank English again. So the next talk is by Zilo Tian, who was from EPFL and is now at the University of Zurich. And she's going to talk about multi-stage, vertex-centric programming for agent-based simulations.
Thank you for the introduction. Yeah, so the title of my talk today is Multi-Stage Vertex-Centric Programming for Agent-Based Simulations. Some of these terms may sound unfamiliar to a lot of you, such as vertex-centric programming and agent-based simulations, and we'll start by explaining what these are. So what is vertex-centric programming? This is a programming paradigm that makes parallel graph processing simple. So graph processing is central to many real-world applications. Big tech industries like Facebook, Google, they all have at its core some performing graph-based analysis for their products, such as Google Map, obviously. But parallel graph algorithms are very difficult to design in the traditional top-down approach. Imagine, so the developers, when they try to write a concurrent program for such distributed graphs, it's really very difficult given the scale. So Prego, which is an internal tool from Google, advocated for this vertex-centric programming paradigm. This really takes a bottom-up approach. So instead of defining a parallel program where you actually need to aggregate certain global information, users define a single sequential program that describes the local behavior of a vertex in the distributed graph. And this local vertex interacts with other vertices to actually perform computations required for a given graph algorithm on a distributed system. And this works surprisingly well and scales to really large-scale graphs. And this programming paradigm has been widely adopted by many open source frameworks. So Prego is not open source, but Giraffe is an open source implementation of Prego. And similarly, it's also adopted by GraphX, which is built on top of Spark, and also Apache Flink. The computational model of this vertex-centric programming is based on bulk synchronous parallel. So this is an abstract machine model which basically says the computations of such a concurrent program will proceed in a sequence of supersteps separated by global synchronizations. So per superstep, each core or per vertex in our vertex-centric context, they can process messages from other vertices, perform local computations that update its own state, and send messages to other vertices. It's very simple, straightforward, and this forms the core computational model for Prego and other vertex-centric frameworks. Now, what are agent-based simulations? Well, agent-based simulations are fine-grained modeling. So conceptually, we can imagine that we have many little AIs, each with its own thread and state, and performing some arbitrary computations. So these little agents, they live and interact in such a virtual world. To really understand what agent-based simulation is, it's important to point out what it's not. So we can contrast with the coarse-grained modeling, such as the classic SIR model in academics. So in such classic modeling, people will describe certain simulation behavior as a set of differential equations. So in this case, different variables are described as the changes with respect to time. The problem with such coarse-grained modeling is that it's very difficult if you want to adjust the behavior. So for instance, if you want to investigate, well, now what happens if people actually travel around, right? Or what happens if some new policy is introduced which changes people's contact behavior, right? So if people are now, with a quarantine policy, they're staying more time at home instead of interacting with others. It requires non-trivial changes to the differential equation models, but such changes are very simple to adapt in agent-based simulation models. And it's the flexibility of agent-based simulation that really gained its popularity among many domains. So agent-based simulation has been around since 1970s, and it has been widely used in many domains, such as academics, economics, and many others. Of course, we as computer scientists care about it because it's actually a wide open area for us as well. So there are many challenges associated with agent-based simulations that are of relevance to computer science. So for instance, as a distributed system challenge, it's non-trivial if you want to simulate billions of agents who are actively interacting and communicating with each other. Existing frameworks such as Spark, they are usually optimized for data-intensive, where there is basically assumes there is no communication among different data nodes. And the synchronization associated with such systems is also very costly. So to have an efficient execution of such large-scale simulation, it still remains a challenge for distributed systems. It's also an interesting data management challenge, because people don't run simulation just for the sake of modeling, right? People want to answer questions. So given an epidemic simulation, I want to know, okay, what can I do to, say, reduce the number of infected population by half, right? So if I want to evaluate different effectiveness of various policies, people want to have an easy-to-express language that can describe a query language that can directly integrate it into such simulation modeling. It's also interesting for machine learning community where people can really use simulations as complex learning models. And some agents have actually lots of latent variables that contribute to the overall result. But of course, for the focus of the talk today, we will mainly talk about the challenge that's relevant to programming, to the programming language community, and which is the focus of this talk. But there are also like compile optimization opportunities in the domain. So given that this field is very wide open, we'll start by saying what we assume in the scope of this paper. So we are assuming that we only consider synchronous agent-based simulations where the semantics, the computational model of such a synchronous agent-based simulation is exactly as defined in the BSP model. All right, so in this case, it's easy to see that, well, an agent can kind of be viewed just as a vertex, right? It's not so much different. You're performing some computation, and then you're communicating with other agents. Given this assumption, how suitable are existing vertex-centric frameworks, such as Prego, Giraffe, GraphX, and Flink, really for agent-based simulations? So can domain scientists just directly take such frameworks and start running simulation? Are we done? Well, we'll start with an example of what does the state-of-art vertex-centric frameworks look like, all right? So users define a single sequential program, right? So in a usually called compute method. And this compute method is repeated code in each superstep during the execution. So the classic example is the PageRank example, where each vertex basically sends its own calculated PageRank value to neighbors and aggregates the values from the incoming links and update its own PageRank value. So here we clearly see that in red, if you want to have different behavior that's dependent on superstep, right? If you say, well, in the first superstep, because I don't really have an incoming message yet, so all I want to do is just send out my message, my value to other vertices, right? If you want to specify this behavior, you really need to add a branch to dispatch on the value of superstep just to describe this behavior. And in the particular case of PageRank, because there is no obvious terminating condition, it can kind of just run forever. So if you actually want to say, well, the simulation runs only for 30 supersteps, you have to add a conditional branch to say, look, I'm actually checking for if superstep is less than 30, otherwise I vote hot. So clearly, we can already see that since this particular compute method is repeated code in each superstep, it's kind of inefficient to always compare these branches when you clearly know that in the next round, the superstep value has already changed, right? So there, we see that there is some inefficiency associated with the dispatching overhead, and it really does not scale as the control flow becomes more complex. It's very easy to make mistakes. This particular instruction, vote to hot here, is specific to Prego or existing vertex-centric programs. So this is a way for a vertex to say whether I'm active or inactive. And the terminating condition is that it will stop when all vertices become inactive. So for the scope of our talk today, we will actually assume that we don't have this instruction, okay? We're assuming, well, the simulation should just run for a given value as user-defined. So this is desirable for simulations because imagine you have an epidemic simulation, right? You can say, well, if a person is infected, then this person wants to remain at home for 5 days without interacting with anyone. But you don't want this simulation to terminate just because if everyone is infected and staying at home. You still want it to run, say, for 200 rounds or something. So we will also assume that we do not have this instruction, vote to hot. Now, as I just explained, so one clear limitation of this is it scales very poorly as the control flow becomes complex. This permits erroneous programs where instructions for different supersteps can be defined at a wrong value. So consider the very simple traffic light example. If you just want to say the color of the traffic light changes as the time proceeds, you can totally define a syntactically correct but semantically wrong program like this, and it will execute. And it's very difficult to debug if you actually allow this to execute in a real simulation. So we want to forbid this. Well, one obvious solution is that we can introduce a binding construct, right? We say, well, the problem of that is we don't have an explicit binding construct specifies what instructions are allowed to execute for a particular superstep. How about we introduce this? So this is a rewrite of the previous example using this binding construct, which we call SC. And we see that now the compute method basically contains what are the instructions that need to be executed in different supersteps as the simulation proceeds. Okay, this seems fine, but it can actually cause code duplication. So it's also the traffic light simulation example is simple enough to illustrate the problem of this erroneous program. It actually, if the binding construct can actually cause duplication for more complex program when closures in different supersteps actually need to share instructions. So if we revisit the previous PageRank example and rewrite it using our newly introduced binding construct, we see that instructions highlighted in red are actually repeated in both the closure specified for superstep 0 and for later supersteps. And this duplication is not there when we in the original vertex-centric model, right? So there, we have a conditional branch to check what the current superstep value is, but we didn't have to duplicate these instructions. So to avoid this, we basically let each superstep execute an arbitrary number of closures instead of a single one. And at the end of each such closures, we pass the continuation index. So this is an example of how we change the previous PageRank example with duplicated code into a non-duplicated code version. So we see that this here at the end of the first super step, we set yield equals true, and then say, well, we should continue with the index 1. And then in the closure for 1, we do not set any yield because this will actually continue with the next super step. Okay, this seems to address our concern concerning duplicated instruction and erroneous programs, but it seems very complicated and it's not very easy to write. So we really want to generate such closures automatically, and we achieve that by introducing a coroutine-like staging time wait instruction. So instructions defined in compute are lifted to a normal form, which basically binds the intermediate values to avoid duplicate instructions. So each instruction is basically translated into a closure, and then the sequence of closure is separated by this wait instruction. So here is an example of the same PageRank example written with the wait instruction. So we see that here we have, by wait simply separates what are the instructions that are executed in different super steps, and we get rid of the conditional branch and duplicated code entirely. So this wait instruction is actually part of it's integrated into a larger system, so it's part of DSL of the front end of our system called Cloud City. So this is a large-scale agent-based simulation framework. So here is an overall architecture of the system, and where the wait instruction is part of the DSL in the front end. So we evaluated this approach by stress test the number of branches, the impact of number of branches through micro benchmarking. And we consider both one-level nesting and two-level nesting, so you have different branching patterns. And we show that as we increase the number of branches from 5 to 20, the overall stage experiments perform better with lower variance comparing to unstaged experiments. So that concludes my talk. Thank you. Yeah, please.
Thanks for the talk. I just had a very quick clarification question about slide 12. About slide 12,
Sure.
like the closure at the bottom there.
Yeah.
When did yield actually? When would yield become true there?
Yield is set true inside here.
Okay.
Yeah. So your question is when it becomes true?
Yeah, but I thought the compute was a different closure, or no, it isn't.
No, the
Oh, okay.
compute here is executing instructions defined in the
Oh,
IC.
okay, right. Yeah,
Yeah,
okay.
yeah.
Yeah.
So yield is defined globally then?
Yes.
Okay.
Yeah.
Yeah, thank you.
Yeah.
I got a bit confused. So if you go to slide 15, I think.
This
Sorry, then 14. Yeah. So so then this is what the user will write.
Yes.
Am I right? So the SC continuation thing that you introduced. So this thing is going to be rewritten in terms of that.
Yes. So this is the front end, and it will generate after lifting. This will generate the closures like as we show in the previous slide. So this will be the generated code, and this is the front end.
And on that generated thing, can you tell us a bit about the staging types? So which types are going to be staged away?
So during staging, right, it will analyze the program defined inside this while true loop of compute, and when it sees this wait instruction, This we use the code pattern matching in Squid, and so when we identify this wait instruction, we will set this yield flag to true, basically. This corresponds to my yield equals true statement. And each instruction here actually is lifted into this a normal form, which actually binds, so this will generate, each of this instruction will actually generate a closure. But then we have some compile optimization to merge the closures when they are just A goes to B, B goes to C, when there's no branching. You just merge those small closures into a bigger one. So after merging, it will look just like that. So the only continuation index you're passing is when you actually have this kind of control flow changes, or you have the yield like change of this super step.
I see. So if I'm not mistaken, then this is the kind of final code that you will generate. You will not apply further optimizations on top of this.
Right, this is the generated code.
Any other questions? If not, let's thank Thilo again. Yeah. This concludes the first session, and see you after lunch for the second session. I'm okay with all options. I'll take my
Sì, e a
yourself the whole time you look over there, right? Five, 10 and 5, so you sort of know. And that will be till till your 30 minutes, right? So if you want 10 minutes per question or 5, you can sort of do them over the tick.
Yeah, I planned it to be like 20 minutes, so I stopped at
Oh,
here. Yeah, that's definitely. You also don't have notes on the slides. I get every time surprised.
yes.
With
Yeah,
notes.
yeah, it's just like too much to see.
And then it'd be like, its expansion on a more higher level, namely on those syntax nodes, which you can see here. So here on the right you have a representation of our macro body as this syntax tree, which then gets expanded into the language. The advantage here is that with lexical macros you could introduce errors, syntactical errors, while with the syntax macros you can ensure that you do not introduce syntactical errors. We will be focusing on the pattern-based and the syntactical macros. So let's dive into the architecture description languages. Well, the big domain is, of course, the domain-specific languages, so it's a subgroup of this domain-specific language group. And they're used to describe something, describe a system. And that's very important. We do not want to execute anything. It should purely be a language where it describes something. And this is also why we did not want to use the procedural approach, but the pattern-based approach. Why you need this? Well, you can generate certain artifacts with it and verify those artifacts. And then there is this distinction between implementing it as part of a host language or have it as a standalone language. For our Vienna architecture description language, we chose the standalone approach, and it is a processor description language. So this is even a smaller part of the ADL family. So it is used to describe a processor. It is work in progress, and why did I highlight it? Well, it's very nice to have this macro system to test out different features we would like to have for our main language. So here, these two parts can play very well together and drive each other. Here you have a quick overview. So left-hand side, you have the specifications, which go into our tool. The specifications are written in Vadel, so we called the tool and the language the same name. And on the right, you have the generated artifacts. We will be focusing on the instruction set architecture specification in Vadel, and also designed the macro system around it. So how does this look? In the instruction set architecture, we want to define the behavior of such instructions. So let's start with a simple add instruction. We have this keyword instruction with an identifier add. Then we have some type information, don't worry about this now, or ever in this talk. Then we have this behavior body, where we have this addition and assign it to the third operand. So what's interesting here is just these parts. Keyword, we have a name, and we have this plus operation from two operands assigning to a third one. Then to have it for to generate an assembler, you need also the assembler, of course, so you specify it in form of these string concatenations and encoding, where you specify the bytes in which you encode it. But this is just to give you an overview on how much code can accumulate just for a simple instruction. And as you can see here, this is just for an add instruction. So what about other binary operator instructions like sub, and or? You would have to repeat this whole process for every one of them. And this is something we do not desire. We do not want to repeat ourselves. So this is where the macro system comes into place. First, we take our instruction. From now on, we will just focus on the instruction behavior to make it much simpler. We take the interesting parts. For us, it's just the name and the operator. We replace it by a placeholder. And now we have our template body. And to use it, and also use it in a type-safe, a syntactical type-safe environment, we wrap it around something which we called a model. So a model for us is this typed template that contains these pattern bodies which have these placeholders. So you can already see here, we use this dollar for switching the context between a language element and a macro element. So let's go quickly over the model. We have the name, the binary instruction, which is the name of the model. Then we have a typed parameter list with ID of the type ID and op of the type bin op. And we get an ISA definition as return type. So these blue types here are syntax types. So those are just types in the realm of macros. So they are just types for the nodes that we parse. They're not in the language per se. So now that we have defined it, how do we use it? Well, we simply call it with this $sign and give it the respective name and the operand. So here, this is how we would use this model and define the add, sub, and or. So far, so good, but what about more complex instructions? So in architectures like ARM, instructions can be predicated. So there is this if statement here that would only execute the instruction behavior if the condition is true. Here it would be that it checks a condition flag. This could be a compare before this instruction. And in our case, it only executes if the compare before this instruction was equal. This brings us, so these are the interesting parts now. And this brings us to the problem that for the ARC32, we have 15 different of these condition flags. So let's try to pack this into our macro system. If we try it with a very naive approach and simply extend our binary instruction, we derive something like this. So extend ID here is a lexical extension we added so that we can have this, so we can generate new IDs in a way that we can control the ID name. So here it would simply do a string concatenation and return an ID in the syntactical manner in a very safe way. So we extended our model with a condition and a postfix. As you can see, there are just IDs and a string. Now, when we start now specifying each instruction, we quickly realize, okay, this cannot be the way. This is too much code we write here. We write 15 times each binary instruction we have. So what we came up with as solution to our system is this higher order macro concept. So first, we take a look at what we already have. So we have this very generic version of our binary instruction template, which we like a lot, but it can be improved. So first, we separate the concerns. So we generate our type composition or these record types where we have like one for the instruction information with the field ID and operand, and one for the condition information with ID and the postfix. Now we can use this, the names as types in our model. How do we use them inside of the body? Well, they're simply accessed as any record. So you have like the name, dot, and then you access the field. How do we give it to the model now? Well, we simply put it inside of parameters and the magic happens itself. So it has to be in that specific order as we defined the names, but this is how it would be done. And now we have it in a more abstract way, but we still have this, we still have to write a lot. So our idea is now to only once specify the different conditions and give this wrapper that specifies these conditions our binary instruction as argument. So first we have to kind of, or first we want to abstract a little bit the type of our binary instruction model, which is here represented with this inst type. So this is now a function type taking an inst info and a cont info and produces an ISA definition. So the inst type would represent the model binary instruction in the type sense. And now to the wrapper. The wrapper, and this is now the higher order, what we call it for the macro, can take now any model of this particular inst type as argument, which we can see here as inst type, and can then use it inside of its body. And now this is now comes the advantage here. So with this wrapper, we can now have this instant model called 15 times with our specific conditions on the right. So we pass it an information, this gets just passed through, and we generate it only, like we write only once the 15 conditions, and those get passed to every model we call our condition wrapper. Now, how can you call it? Well, you have this model binary instruction we defined before, you have our condition wrapper, and now you just call the condition wrapper and give it the binary model as argument, and then you give it the specific instruction informations. And as you can see now, we arrived at the same amount of code, but encoded a lot more of complexity as before. And what's here also interesting to notice, this approach, just for binary instruction, you could simply call it inside of the template just with binary instruction. But with this approach, you can give it any model with this type. So you just define this condition wrapper once, and then you can give it not only binary instruction. For example, if you have a different behavior for shifts, or if you have a unary instruction that has like the similar setup with operator and ID, you can put it in here, and the wrapper will call the underlying instruction with the correct arguments. Now for the evaluation. We implemented this in our tool and tested it with our instruction set architecture specification, or more specifications. So those are the fours listed here. And we were interested in runtime and code size. So first, we simply took the number of lines. So in green, you see a program that has these macros in it. And in blue, you see a program where these macros got expanded and then printed again. So blue is without macros, green is with macros. The Y scale is logarithmic, so this is even more impressive. And you can see for the ARC32 and ARC64, we have like a lot of improvement here. For MIPS and RISC-V, this is slightly less, and as you can see here, especially for RISC, somehow we end up with more code when we have macros and less code in the expanded way, but this has a reason. And the reason for it is that the number of lines is a very bad metric for defining the usefulness. So we came up with we used a new metric in the paper, which basically just takes the syntax nodes, and now we can see that indeed for RISC, these very long one-liners now take no part anymore, and we just use the syntax nodes, and we can see that we actually have like less code to write than it is produced. Something interesting maybe is the runtime here, and while for MIPS and RISC, the runtime is very similar to each other. So we have in green the parsing, in orange we have a macro expansion, and in blue we have the parsing again with the expanded version of our program. So there are no macros here, it would be the long program. And here you can see for MIPS and RISC it doesn't really matter, but for ARC64 and ARC32 it matters, because in ARC32 it was actually faster to have macros and expand it in memory than parsing the huge file that is generated by the macro. And for ARC64, even though the runtime would be the same for the expansion, the parsing runtime is not the same. And since we use this syntactically typed macros, every second we save in parsing time, we get a faster IDE feedback. So this can improve like the IDE performance. Okay, so what are the final takeaways here? Well, a macro system, especially the syntactically pattern-based macro system, is great for specification languages. They make it much, it can be faster when the things you want to describe are complex enough, so to say, and it makes it definitely more concise. In this talk, I showed you this model element we had, which is this syntax type saved higher order macro template, and I showed you the record and the model type, which is basically the composition, like syntax types composition and the type alias. Thank you very much.
Thank you. You have questions?
Thank you. I'm Eric Heide from the University of Utah. Thank you for your talk. It's very interesting. So I don't know your domain very well, but my belief is that CPUs are often, they often have quirks and irregularities. Like for instance, you know, some instructions might not be available in all of their predicated variants for various architectural reasons, right? So there are 15 flags, but some instructions might be predicated on all, you know, there might be predicated variants of all of them for some flags, but some might only be available, say only 5 of them are actually implemented on the core. And I guess, so first, my question is do you encounter that problem? Is that an actual problem? And second, do you have a way in your macro system to deal with that sort of thing easily?
Yes, very good questions. So the first thing is, yes, like we encountered where the semantics differ a little. For example, for shifts we had this problem, this challenge where it's, some architectures required the shifts to be like casted to a certain value before having it as the operator. And this, like there are similar approaches how we handled this. For example, you could just make a separate, very generic version of your shift family of instructions, and then you can simply put it in there and it does it magic. Or you can, for example, model this, this cast as an expression which you provide as parameter, and you can then, with like some clever ways, you could then only have it be used for a specific family of instructions. Yeah, so the second question, I think it was already a little bit answered right now with how we would deal with it. We have more in our language, which I did not present yet now, which is basically we have some kind of conditions. So we have like a pattern matching for different syntax nodes. So if a node is, for example, if you provide an ID, then we can pattern match on that ID, and if that ID has a certain name, for example, then shift, we apply other behavior than for others.
I actually, one more question. I didn't see a hand up. Oh, there's the hand. So your actual macros are, maybe they have a little bit more parameters than what you showed on the slide. So in particular, you had a semantic function, you had an assembler syntax, you had a binary encoding, maybe there was a fourth thing. I mean, so presumably you would have to specify all of these things as parameters to your models, right?
Yeah. So basically, this is why we had it before without this composition, so without these records, and it was like huge. The parameter list was too much to be efficiently debugged. So then we introduced these record types to get a hold of this. And now with these record types, we have the separation of concerns. So now when we define something new for conditions, we simply have to look at this record for the conditions. Yeah, but yeah, we encountered this. It was, before it was a lot to read.
Hi, I'm Sulu from University of Zurich. Very interesting talk. So given the heterogeneity of hardware, right, so I understand this is about specification, right, but do you kind of imagine you can, because a lot of, say, compiler optimizations, right, they are kind of, so regardless of whether you can have like specific implementation details regarding, say, add or vector, certain vector instructions, right, but there are certain common compiler optimizations that can be applied to such, say, vectorized computations regardless of the actual implementation, like the architecture details, right? Do you imagine this language, like this kind of specification, can also be combined with certain computations, like you can actually push that into certain compiler pipeline to enable some generalized optimization so that you can perform certain generalized optimization in an architecture-independent manner?
Okay, so if I've understood this question now correctly, it was, okay, so this talk was more about this macro system, but I think the question you gave is more about the specification language, right? Or
right, so like whether you can, I guess my question is, because right now, like the compiler is really kind of, you know, it's architecture dependent, right? So you have some, say you are optimized for this Intel version of GCC, or you're optimized for the RISC-V, right? And then, but there are certain overlapping at certain abstraction level. So for example, in your case, is this at the specification level, right? So do you kind of see there are certain ways you can bridge the gap?
Yeah, so there's, so specifically for the macro system, it would be then that you can, you can also give it flags via the command line. And then, for example, you can say, okay, generate me now a specification that is specialized for the GCC compiler, or generate me a specification that is specialized for CLang, or just a specification which is used, for example, for this optimization steps. But in our case, it's more on seeing where the macro system can guide our language. So when we see, okay, we use this a lot and it makes sense to implement it in our language, then it would, for example, your question would be, I think, better solved in our actual architecture description language than in doing it with macros. So then you have like different entries in our language where it's handled there, yeah.
So in the title, you mentioned the macro thing being LL regular, and that just didn't seem to factor into the rest of the talk very much. So I was wondering if you wanted to say a bit about that.
Yes. Yes, it kind of stayed within the name of the paper and within the talk. I thought it is not really relevant to get the bigger picture. I can go into this, yeah. So basically the pred LL star is there because we use, for our internals, we use the xtext and xtend, if you know this framework. And they have this answer parser underneath, which is LL star. And we used the predicates to track our names of the models. So we have this top-down parsing. And when we encounter a model, we saved just simply this name into a table, and then it continues top-down parsing. And when this name is used, then just a very small predicate is checked here if this name already occurred in this scoping. Yeah, but that's an interesting question, because we had it once without just LLK parsable, and to be like the step between those two are very small. To make it LLK parsable, you would just have to give it like type hints. You would just have to say, okay, this what you encounter now is, for example, a binary operator, but then you shift the problem into the expansion. So then you have like this LLK parsable language, but then in your expansion you can encounter these symbol clashes or something like this. So, yeah.
Yeah, maybe one more quick one.
Just a very quick one. So accidental name capture has always been a problem with macro systems, and I was wondering, when you render your macro system higher order, do you exacerbate the problem, or do you have particular provisions against it?
Yeah, that's also an excellent question, because we were thinking about making it hygienic, but we decided against it because there's just two reasons. The first reason is that we actually want to capture names. So when we generate, for example, this instruction, I want this X before the operator. It means a register definition that is somewhere done somewhere else before it, or below it, like in this, the order doesn't matter here. And we want to capture this X. So this is the first thing. And the second thing, for every new identifier, we do not need an generate random identifier, because we sometimes want to use the name again somewhere else. So we wanted full control over this name. And also in the generated artifacts, it makes it much more readable when you have full control over your name and you just append like a postfix, as we did in the example here.
But you do have a gensim or somewhere as well, if needed.
It's not implemented, but of course you can, yeah, you can extend it, yes.
All right, thank you very much. checkers. Casper?
Yeah, thanks. I'm Casper. This is joint work with Aaron and Paul. And well, as the name suggests, this talk is going to be about name resolution and multi-phase type checking. In general, when we implement type checkers or programming languages, we actually typically need to resolve names in multiple phases. This may be something that you're not very used to thinking about because typing rules tend to abstract from this fact. They tend to abstract away the details needed to construct the necessary information that you need to type check languages. So for example, here is Featherweight Java. This is an excerpt from Pierce's Types and Programming Languages book. In order to define name resolution for Featherweight Java, Pierce says we assume the existence of a class table, and the class table tells us what is the structure of each class. And using this structure, well, we can define what it means to resolve a name. This is great for a declarative specification. We can read and we can understand how name resolution works precisely in Java. And we don't have to think about how this class table is being constructed. We can understand it completely independently. But if we are to implement a type checker, the order in which we fill in this class table is going to be very important for getting the semantics of name resolution right. Do we implement the right notion of name resolution? Do we implement the type checker that respects the typing rules, basically? And as it turns out, resolving names in general in type checker implementations does require phase name resolution. It requires you to construct this name binding information in a careful way, otherwise your type checker will be wrong. And to illustrate this fact, here is a Java program. We have a class A and an integer field x, and an inner class B, a class y that references the x that comes from the lexical context. Then we also have a class C that we're not using yet. When we initialize the inner class here, we are going to get 0 as the result because the x in the inner class references the x in the outer lexical scope. If we change this program to now use an extends clause so that the inner class now extends C, we have actually changed the semantics of our program. Name resolution is now different. The name x now resolves through this extends clause to the x down here. We can understand how name resolution works by alluding to a class table. So here's an example of a class table for Java. We have 3 rows in the table for the 3 classes that we have. The class table tracks what are the extends clauses for each class. It tracks what is the lexical context for each class so that we can resolve through that if we need it. And then we have the fields and the methods. And the reason why the X resolves through the extends clause is that, well, the extends clause for B has a C. And so C has a field X, and so we never resolve through the lexical context because bindings in extends clauses take precedence over bindings in the lexical context. So this is the name resolution for Java. We can understand it completely separately from phasing concerns. Now let's consider how actually not to type check this program. Let's consider what happens if we implement phasing wrongly and we construct this table in a wrongly phased manner. Let's start with a class table that has just 3 rows. We have a row for each class that the program contains. And then we just start filling in the class table as we go through the program. We start by looking at the class A. We fill in the extends clause. We fill in the lexical context. We fill in the fields, and actually as we encounter this field, we will also type check the right-hand side of the field initialization expression. So here we have just a 0, so that means that, well, that's trivially compatible with its type. Next, well, we proceed to type check the class B, and we inhabit a part of the class table related to this. And we're now ready to type check the right-hand side of our field Y. This right-hand side references an X. And in this broken type checker, I haven't filled in the part of the symbol table that has to do with the class C. So even though I have an extends clause that references a C, my class table is uninhabited. The fields are uninhabited for class C as of yet. And that means that I can resolve this X, and I will resolve this X even though I have a type checker that implements all the right checks, that looks in the class table in the right way. I have phased it in the wrong way, so the class table isn't complete yet. So this phasing error will not give rise to a runtime, a type checking error. I will actually resolve the name, but I will resolve it to something that is not the thing that I was looking for. I will not respect the name resolution semantics of Java. So this is a subtle class of phasing and name binding error. And the contribution of our paper is that we provide a framework for defining name resolution in type checkers in general, not just for type checkers that have class tables, but also for languages that have general scoping constructs, such as packages or modules, what have you. And then we provide a new approach to detecting and rejecting this subtle class of name binding error that I just showed you, where we silently resolve to the wrong thing. If we resolve to the wrong thing, our framework will detect and reject and notify the type checker engineer that something is wrong. You implemented your specification wrongly. And finally, we provide techniques that reduce the gap between specification and implementation. So using our techniques, we can write multi-phased type checker implementations, which is what you need in order to resolve names in general. But then there's a gap between that and the declarative specification, which does not involve phases. And we provide techniques that reduce this gap. So this is what you'll find in the paper. In the rest of the talk, I'll try to give a flavor of each of these contributions. To give you a flavor of this, the framework that we use is, I'll change the object language that we use. Here I have the same program as before, but now in a module language. I have a module A binds a field X, a module B that imports C. I have a field Y that references an X, which could either reference the X from the lexical context, or it could reference the X that comes from the import, exactly as before. The framework that we provide in the paper is based on scope graphs. So what a scope graph is it is essentially a data structure for representing name binding information. Whenever you have, it's going to contain the same information that is in a class table or a module table or a symbol table that you may know from compilers. But it's going to lay out this information in a graph. The observation here being that actually when you have a class table, it contains cells that reference each other in a way that really represents a graph. And if we represent it as a graph, we can represent name resolution as a graph search problem. So this is the idea behind scope graphs. And I'll now give you a flavor of how scope graphs work. So we will type check our simple module language here in 3 phases. The first phase, we will just look at the modules and the members and construct the scoping structure of those. Second phase, we will resolve the imports. And in the final phase, we will type check the right-hand sides of definitions. So we start by just considering the first module that we have. This is module A. This constructs this piece of scope graph over here, where circle nodes represent scopes. So here we have a root scope, which has a declaration for the A module over here. This declaration is associated with the scope of the module, so that whenever we resolve to something of type A, we can access, and we know what is the scoping structure of A. So A, in turn, is also a scope. The scope is A. It has a single declaration for the single field that A binds. And we have an edge that connects the scope of A, the scope of the module, to the lexical root scope, which makes all the bindings that are reachable from the root scope are now also reachable from scope SA. So this way, by connecting the scopes, we can really model visibility and reachability policies. Proceeding with type checking, well, we do this exercise for all of the scopes that are, all of the modules that are in this program. So the next module to consider is module B. Again, we create a new scope for module B. This scope has scope A, the scope of module A as its lexical parent. We get a declaration for the module B inside of our module A, and we get a module member for the scope of B. And finally, for module C, well, it's the same idea as before. So that was phase 1. We've constructed a part of our scope graph. We've constructed the part of our scope graph that just considers the modules and members. in the next phase, we are ready to now start resolving imports. Now we know what all of the modules are and what their names are, and now we can resolve named imports. Here we have a named import that is referencing something by the name C. Well, in order to figure out what this C is, we have to do name resolution. We have to resolve the name C, and assuming we've constructed enough of our scope graph, which we have, we can resolve the name C. And the way we resolve this name is as a search through the graph. The search through the graph is basically saying, well, we have a query here, which says we are looking for something starting in scope, the scope of B. The thing we're looking for is a C. And then the path that we're looking for through the graph should have this shape. We can follow lexical parent edges. We can follow a single import step, which defines the name resolution policy of this language that we've defined. We are allowed to follow a single import step, and then we should be able to find our name. And then, we should find the module. The last argument that we have here is an ordering predicate, which allows us to compare paths. So if we have multiple possible ways of resolving the same name, we can decide which name we prefer by looking at the paths and comparing them, and basically implementing name shadowing in this way. In this case, well, the thing that C resolves to is the C down here. So what we do is we add an import edge in phase 2 from the scope of B to the scope of C, such that all of the things that are in C are now reachable from scope SB, which is how imports behave. And now we're ready to finally type check the bodies of our definitions. In order to type check the two x's, well, they're trivial because they're both ints. So the interesting case is the case for the y here. In order to type check the right-hand side, well, we have to resolve this x. Again, we perform a query through the graph, and we figure out that there are actually two ways of resolving this x. And our ordering predicate, which I haven't spelled out, will prefer paths that traverse import edges over paths that traverse lexical parent edges, thereby implementing the right name binding policy for our language. So all that I've shown you is basically standard scope graphs. This is all based on previous work. A new thing here is that we have embedded this in Haskell. We've embedded it, this is why we call it a monadic framework. We've embedded it in these 4 operations. We have a new operation for creating a new scope, an edge operation for creating a new edge, sync operation for creating a declaration, and a query operation for querying the scope graph. This is all you need to do name resolution in any programming language, really. What I haven't talked about yet is how does this help us with this subtle name binding error, this subtle phasing error that we considered in the beginning of the talk. So actually our 4 operations help us detect and reject subtle errors, like the one I showed you earlier. So to illustrate that, let's consider how we can type check our program again by not using 3 phases, but just using some differently phased approach that will resolve names in the wrong way. And then how this will allow us to actually detect and reject this kind of phasing error. So we start by type checking module A. That will create the module structure of A, exactly as before. Next, let's say that we actually type check the right-hand side of our definition. So here we type check, well, 0 is an integer, boring. Moving on, we type check the module B and create the scope graph structure for the module B. And we don't resolve the import of C just yet. Instead, we start type checking the right-hand, we start type checking this definition down here, and we start type checking this X. So this is exactly the same problem that we had with the class table example from before. When we query the scope graph is incomplete. The information that we have about a program is incomplete, and so the X that we resolve to will be the X from the lexical context. This is the wrong resolution of X. The way our monadic framework works is it will actually allow this for now. And then later on, when we add the import, we will detect that the import was added and a new path becomes available, and we will reject the program. So let's continue and see when this happens. We start type checking module C. That will create the module structure of module C. And then finally, well, we'll type check the right-hand side of X as well. Finally, we are ready to start resolving the import C, which when we resolve it, well, we figure out that this is the C that we want. We add an import edge, exactly as we did before in our graph, which makes all of a sudden a new path available for the previous query that we ran. The previous query for X, which before resolved to this thing, now actually resolves to this thing. So dynamically, during type checking, our monadic operations that we provide for scope graph construction, check whenever you add new structure to your scope graph or to your class table, if you will, to your symbol table, whatever, you check, does this violate previous resolutions for any of the names that I knew about? And if it does provide new paths that shadow the old ones, we raise an error, and the type checker engineer can now know that there is a problem in the program. It doesn't silently return the wrong thing. We will reject this program as containing a phasing error that is really in the implementation of our type checker. All of this happens behind the scenes in these 4 operations. So all you have to worry about when you're programming against our interface is you have to know that these 4 operations construct scope graphs. And whenever you make a query, you can be guaranteed that the query is going to be stable in the final graph, or you will get an error notifying you that you have made an error. So you can sleep better at night. Okay, so that was basically the second contribution point here, a new approach to detecting and rejecting phasing errors in type checkers. The final the final contribution that I have here on the slides is that we provide techniques that reduce the gap between declarative faceless typing rules and multi-phased type checker implementations. So using the operations that I've shown you so far, I can write type checkers that could look something like this. This is a type checker for the module language that I showed you before. Here I'm using a top-level orchestration function for first creating a lexical root scope. That's the first line here. Then I'm calling a modules function, which represents the phase 1, which will create all the module structure, the scoping structure of my programs, and postpone the type checking of imports and the type checking of right-hand sides of definitions. So I'll get 2 queues, 2 working queues representing these delayed constraints. And then I can first do the imports in phase 2 and then finally do the members in the final step. So this is a fine type checker. It will behave exactly as I intend. But it's not at all obvious how this is connected to a declarative specification that I could write for my module language. So here is a declarative specification using scope graphs shown on the right here. A module here is well typed according to this typing rule. Whenever I have a module scope that exists in the graph, that's what this nabla here represents. By the way, these typing rules are borrowed from previous work on this module that describes this module language. And if in the scope that I'm in, there is a declaration for the X, and if my set of module members are well typed under my module scope, then the program, then my module is well typed. So each of these rules do not talk at all about ordering. They just talk about the scope graph having the right shape, just like the featherweight Java rule that I showed in the beginning talks about the class table having the right shape. And the question here is, how does this relate to this very explicitly phased implementation that I have on the left? In particular, one of the challenging rules here is that actually for this def rule here, I said that in phase 1, I actually want to construct the entire scoping structure of my module except for imports. Well, that means that this constraint should really be run in phase 1. And this constraint checking that the right-hand side of a def is well typed should only happen in phase 3. So my premises here are scattered across my type checker. There's a gap between the specification and the implementation. I won't have time to go into all the details of how our framework works, but a key ingredient that we provide in helping bridge the gap between specification and implementation is that we use applicative functors. So all of the definitions that I've shown you so far, we're using monads in Haskell. So that is that we're using these two interfaces summarized up here. We are now going to be programming against a slightly richer interface. We're going to be programming against an interface of applicative functors. Here I've phrased that as monoidal functors. It's equivalent to what you'll find in Haskell as applicative functors. We're going to use functor composition, again, a standard definition that you'll find in the Haskell standard library. And then we're going to use these slightly less standard combinators for phasing computations. The here computation says if I have a computation, a phase 1 computation, I can treat that as a multi-phase computation where F is the first phase and G is the second phase. And there can be used to inject a computation in phase 2 into a multi-phase computation. And then I provide these custom bind operations here, which allow me to compose multi-phase computations. So the first one here says, well, if I have a phase 1 computation and I have a phase 2 computation that depends on the value of the first computation, I can combine them into multi-phase computation. And this second one says, if I have a first phase computation and something that has and a multi-phase computation as a continuation, provided F is a monad, I can combine these. So these are the combinators that we use, that we provide for now programming type checkers in a slightly richer way that lets us define and compositionally map abstract syntax trees directly onto their typing constraints. So again, I won't have time to go into all of these cases. The main point that I want to make here is that whereas before I had typing constraints that were scattered across different functions in different phases, I can now say precisely in each case of my type checker that this abstract syntax tree has these typing constraints, and then I can use my monadic combinators, my applicative combinators to specify precisely the order in which these different constraints need to run and compose them in a way that respects the phasing order. So this is all based on it's inspired by previous work by Gibbons, Kidney, and Schrijvers and Wu, but we have a spin on it. For the details of how this works, well, you could ask me but I think it's better to perhaps look at the paper. So in the paper you will find more details of how and why this works. You'll also find 2 case studies. The first case study is for LM, the simple module language that I've shown you. And while it may look like a very simple module language, it actually has a very sophisticated import feature that has import-sensitive name resolution. That means that whenever you import something, it may affect previous imports. While this sounds like a contrived and challenging feature, it is actually a feature that turns up in a microcosm version in the Rust compiler, which does name resolution in a way that is very careful to phase the imports in the right way. It's also a feature that previous work on scope graphs was unable to express. So previous work on scope graphs on the meta-language statics, which allows you to basically derive type checkers from rules that look close to this. That meta-language is not able to express this case study that we are able to express with these combinators. This is the second case study that we provide here is for the Mass-Hindley-Milnor type inference, which is another example of a feature that was unknown how to type check with statics, this previous meta-language. It does not involve phasing per se, but it is important that you only do unification and generalization in a particular order. You can only generalize over type variables once you know that you've fully analyzed the lexical context that you're generalizing over. That's all. Happy to take questions. Thank you.
Yes, thank you very much. A very nice explanation of the symbol resolution and the potential conflicts. I'm curious about the dynamic typing, where you explained that, well, you first kind of accept a solution, later when the scope graph is completed, switch it again. So comparing to traditional programming languages or even the typing system or symbol resolution of language workbenches for modeling languages, there I would expect something like, well, we have these different phases, first build up the complete graph and then do the resolution. Compared to that, where is the benefit? Are you more efficient than that because you can dynamically load it, or do I have to care less about my phasing? So just compared to first constructing the whole graph, because then I, of course, should be able to come to the same result.
Yeah, so our goal here is really to try and bridge the gap. It's a twofold goal. We want to try and bridge the gap between specification and implementation. Right? We have typing rules that define our language, and then we want to bring an implementation as close as we can to the typing rules, and while also being as flexible as we can. And we provide added flexibility over previous work on statics. If we are to construct this full graph first, you are basically implementing a completely phased approach, where this graph, I don't know how that would correspond to your to typing rules. Would you then, you are probably going to have typing rules that then would talk about the graph being fully constructed, and you would have phases in your typing rules. And I would argue that that's actually an anti-pattern, and that phasing is an operational concern that we should be abstracting from in typing rules. So I don't know if that answers your question.
Yeah, it answers the question. It was my guess that you should care less about the phasing issues.
Right, right.
Okay, thanks.
Thank you. A clarification question with possibly a question after that. So when you are really resolving already, so in the last phase, in your query, can you also put some type-in information about the thing that you are resolving, about the, for instance, the context of the thing that you are using? I'm thinking of some languages like 4GLs where name per se is not a unique thing. You can have multiple things with the same name, but as long as their types are different, then you will be able to resolve it. So you sort of, you need to look at the place where the thing is used, infer whatever you can from the type, and then you sort of, your start of a guess is enough to resolve it in the table. Can it be done here?
I think it can be done. I would be happy to try it out and brainstorm a bit more in a break. Basically, the query operation that we provide just says, you give me a declaration. I don't care what the declaration is. You give me a predicate that identifies this declaration. So you can write that declaration, you can write this predicate in any way you want. You can write it to do fuzzy matching on both the name and the type if you want. So in principle, that's supported. And you can also have, I mean, these are monadic constraints. You can have backtracking in your monad if you want. Actually, for implementing LM, we do a limited form of backtracking. So I think yes.
Okay, cool. Then I do have a follow-up question, which is, you mentioned that this particular implementation can handle a case study that was not possible to be handled a couple of years ago, when it was also made sort of this soft claim of scope graphs can do everything probably. So now they can do even more, and it's probably everything, but probably. So what else is there that prevents us saying that scope graphs of this particular form can do everything?
That's a good question.
Sorry.
So, yeah, well, so I think that the claim that scope graphs can do everything, I think I will stand by that. You can emulate typing context, right? So anything you can do with the typing context, which is the main alternative, or anything you can do with symbol tables, you can encode that as scope graphs. The thing that you couldn't do in previous work was that, well, we had particular constraints in place because we wanted a declarative specification. Here we're giving up some of that declarativity and gaining a lot of expressiveness in return. So the model is the same, the implementation details are slightly different. It's striking a different point in the design space, putting more responsibility onto the type checker engineer, responsible for actually facing things in the right way, but at least telling him or her if they get their facing wrong. So this is sort of the trade-off. This is the reason why we're striking a different point in the design space, I think. Don't know if that is an answer in the right direction of your question.
It's a step.
Okay.
Thank you.
If you're looking for another challenging case, I recently had to implement name resolution for Ansible infrastructure as code scripts. And over there, you can actually, if you go to your conclusion slide, you had the example. There you can actually, or the module language.
So
yeah,
this one?
Just the conclusion one, no, the two thumbnails.
Yeah.
So within module C, there you could actually replace the def keyword for X with a set fact keyword. And all of a sudden that would take precedence over any other local variable declaration. So would that be supported in the queries? Because it seems to me you would need some kind of negation then in the query language.
I think so. I think it can be done. Again, in order to actually implement this import resolution semantics, what we did was we implemented backtracking, where we sort of roll back, we speculatively add some things to the scope graph, and then it may turn out that that was not the way to do things, and we roll it back and we try over. So this backtracking is compatible with the monad because we are now working in this monad more abstract setting. We have more control. And so I think that you could implement the right control operations that lets you control the scope graph construction. The question is, what are the right operations for this particular feature? And I think that's an interesting question that I don't have the answer offhand to.
It's a nice challenge,
yeah,
I think.
Yeah.
All right, I would say let's thank the speaker, but I have like a bunch of questions. So look, the thing about being a session chair is you don't get to ask your questions because you run up with a deferment to the audience. So I will hound you later, and especially like the, what was it, weekly critical edges, what was that, how does that compare?
Yeah.
But anyway, let's thank our speaker.
Okay.
All right, our next speaker is, my eyes don't deceive me, is Jose. Is that correct? Jose, right? Jose. Excellent. Yes, so as I said, Jose is our next speaker for C2 Taco. So, Jose, please.
Okay. Thank you very much for attending to my talk. Today I'm going to present my most recent work, C2 Taco, Lifting Tensor Code to Taco. So in the last decade, we have seen a large increase in the use of machine learning in a wide range of applications that go from our personal devices to even cloud computers. So it's no exaggeration to say machine learning is everywhere. And machine learning is dominated by tensor algebra. So most of the time, machine learning systems are doing some kind of tensor algebra computation. This means we want the tensor algebra to be fast. We want to generate a fast assembly and executable code for the computation we are performing the most. And current technology still fails to deliver the performance we want by just using general compilers or general purpose languages. We cannot get to the performance that we want, and this has led to the growth of domain-specific languages, which are languages that embed knowledge about the domain they were designed for, so which makes them to be very efficient, so we can get to the fast assembly that we want. One example of such language is Taco, which is the tensor algebra compiler, which is both a high-level programming language and a compiler that generates platform-specific code. And the core of Taco is the ISUM notation language. So the programs in Taco are expressed using Einstein summation notation. This is one example of a program that multiplies a matrix for a vector. We can express like that in Taco. Another example is give this piece of code, which is, although it uses a lot of pointer arithmetic manipulation, this is actually matrix multiplication. And we can express the same code in Taco using the Taco index expression notation, which is the green box on top. And we can give that expression to Taco compiler that generates both high optimized codes, high optimized C code for CPU and CUDA code for GPU platforms. So cool. Given that we have this language, now we can go and write our applications with those languages, then we have the fast code we want. But what about legacy code? What about existing databases of code that we would like to speed up? How do we jump from the existing language to the domain-specific ones? This will involve a lot of rewriting code, and like, no need to say that doing this manually it's error-prone and time-consuming task. So we would like to do that as automatic as possible. And people have tried to build that dash arrow over there over the past few decades with different techniques. One example of such techniques is API matching or rewriting. Is when you detect a piece of code that's performing a computation and then you replace that with a call to some API that was designed by performing that. The problem with that approach is that it's very brittle and it needs to change a lot every time the API changes itself. And you know that usually those APIs, they change by version very fast. So you need to change your API matching approach. Another technique is using neural machine translation, which is using deep learning models to directly translate from one language to the other. The problem with that approach is that it demands data and demands quality data, which is not exactly wide available, especially when we are talking about domain-specific languages. Another technique is called verified lifting, where you can specify the computation using logic formulas, and then using that summary computation, you can translate to your target language. And the problem is that for the domain of tensor algebra, that doesn't apply very well because the problems are just too complicated for the solvers to reason about. And the logic formula you have to create, it becomes too complex and unfeasible to be expressed. So in this context, we propose C2Taco, our lifting tool that will lift tensor code written in C to Taco. And the core of our approach is using enumerative program synthesis from input-output example. So we use programming by example using IO as our specification. So using C2Taco, we can go from that C code to Taco, and then you have optimized versions of the original code. This is the overall architecture of how our system works. So given a program P, we first need to give that program through a program classifier because we take as input general purpose programs, and not all the computation in those programs is expressible in Taco. So we need to detect the regions that are actually expressible in Taco. So we use program classifier to extract the region we call K, regions of code that perform some tensor algebra. We use that to generate IO examples that to serve as specification and give to C2Taco, sorry. And inside our C2Taco, we will have the synthesis part that we use the IO specification plus some code and some code features that we will extract from the original code to help guiding the synthesis search. And once our synthesizers find an equivalent program in Taco, we pick up the program T, we use the Taco compiler, lower it down, and then we can replace the computation in the original program. So we use IO generation as previous work. We use just a methodology that uses value profile files where you can define dimensions of arrays and values of variables that you want to generate I/O examples. And we use bottom-up enumerative synthesis of templates, which means that we are generating programs with template variables and that we need to find valid substitutions for those templates to concrete values from the specification. And our synthesis has an upper bound length, which I should talk about later on how we get this upper bound for our synthesis stop. And so it's basically bottom-up enumerative synthesis. You start with programs with length 1, and then you expand the grammar to programs of length 2 by adding all possibilities of programs and all possibilities of new tensors and constants. As you get to bigger lengths, you also include mathematical operators and so on and so forth. As you go, you just go expanding and having more programs that you explore. As you see, for the example, I just showed the solution. It's there, but there are a lot of programs to be checked. We enumerate all of these programs, and then we check them by looking for substitutions for the template variables we have in the programs to the concrete values we have in the specification. And we either return an equivalent tackle program or we return no solution found. And the search space of programs we can look at, it's enormous. So just simply enumerating all of them is not feasible. What we do is that we leverage the fact that we are going from source code to extract features from that source code that will help to guide our synthesis search. We define 3 analyses. One to detect the length of the program we would like to synthesize, one to detect the order of each tensor in the program, and another one to detect which are the mathematical operators that that are likely to be in our solution. So taking again the example from before, the first analysis program length. Given a program, we will find the relevant statements or relevant computations that we want to express. In this case, we notice that this is the relevant computation of this piece of code. So we will analyze the references in there. We go back to their definitions, and we see that, okay, we have 3 variables, 3 tensors that come from the input. So it's likely that our solution will need 3 tensors. So this is we will come up with the upper bound for our synthesis algorithm from the code analysis. And secondly, we try to guess the order of the tensors in the program. So we do this with a combination of array recovery from pointers and array delinearization. So for example, given that pointer PC, we apply our transformations to get that PC it's actually going over an array by using that affine expression z times k plus I, which give us PCKI, which means, okay, this tensor is likely to be ordered 2. And finally, we just simply analyze the computation we are interested at and see which kind of operators we have that. In that case, we have a multiplication operation. So basically, we give to a synthesizer looking for a program that is equivalent to this one, that behaves according to the specification of this one, but the length is likely to be 3. You will have all the tensors will have ordered 2, and they will include multiplication. So we go enumerating programs again, and again, we'll have more candidates than those, but we will just enumerate programs with length 3 and the tensors with order 2 and multiplication. So although we are still enumerating programs, we are in a very restricted space, and this leads us to find our solution quicker. We compared our approach with 4 different techniques. One of them is which we call ETS, with simple enumerative template synthesis, which is basically C to tackle without the code analysis help. So it's basically bottom-up enumerative synthesis. And we also compare against a neuro-machine translation model where we use the TACO compiler to generate a lot of pairs, TACO ISAM notation, and C. And we use that as training data to train a transformer model that will output the TACO program given a C program. And we also compare against ChatGPT because although it's not trained to output TACO, it's a widely used neuro-machine translation approach, and we want to compare something that we didn't train. And we also compare against TF-Coder, which is an open source synthesizer that also synthesizes programs from input-output examples, and it synthesizes programs in TensorFlow, and we manually check that the search space of TensorFlow is able to represent all the programs in TACO, so it's a valid comparison. We evaluated on two sets of benchmarks. The first one we call artificial benchmarks. They are handcrafted benchmarks that we know for sure can be synthesized. So we performed this evaluation to see how well those approaches do on programs that we know for sure that there is an answer. We have 10 artificial programs, and we can see from this table that TF-Code is able to synthesize 4 of them, and ChatGPT is 5. Our NMT model is able to correctly synthesize 7 out of them. The simple ETS synthesizes 8, and C2TACO is able to correctly synthesize all of them in time. ETS fails for 2 programs because the search space gets too large, which is the same case for TF-Coder. And for ChatGPT and for the NMT model, they just output programs that are, in some cases, for the case of NMT, they are all syntactically valid, but they are semantically wrong. For ChatGPT, you have both cases. You have programs that are syntactically wrong and programs that are semantically wrong. We also test with programs taken from real-world applications with a total of 61 programs. We're taking from different sources that include, for example, digital signal processing benchmarks, machine learning frameworks, and scientific mathematical libraries. First, we evaluate the coverage of each approach, see how much of our whole benchmark suite each approach can lift. We have the result for each one of the sets in our suite with the general mean on the right. We see that NMT was the worst approach, and it wasn't able to lift any program in the real-world code. And we claim that NMT was trained with TACO-generated programs, and they have a similar structure that does not express the general structure of programs that we will find in real-world applications. So the NMT model we trained was not able to reason about different programs. ChatGPT was able to lift 22% of the programs, and TF-Code was able to correctly synthesize 33% of the programs. Both ETS and C2TACO had high coverage, but ETS still fails on more complex programs where the search space gets too large, and C2TACO gets the high coverage, being able to correctly lift 95% of the benchmarks in our suite. For error analysis, we detect 4 categories of errors during our evaluation. We have the semantic errors, which cases where the technical outputs a program which is valid according to the TACO grammar, but it's wrong according to the specification. This is the case for a few programs in ChatGPT and almost 20 programs that TF-Coder outputs, and this is the case for all the programs NMT fails. So we conclude the transformer model is able to correctly capture the structure of the output, so it understands the grammar, but it doesn't understand the meaning of the program it's trying to translate. And we also have syntactic fails where the outputted program is wrong even according to the grammar, and we saw that only ChatGPT produced programs that are syntactically valid, but again, ChatGPT was not trained specific for this, was trained with billions of parameters. They are completely general. We have the large search space, which affects the search-based techniques. It's the main reason of failure for TF coder and the only failure reason for ETS, and we have the C2 tackle failing on unsupported features, which means features from tackle that we are not able to support, which includes sparse code, and for example, sparse code, distribution of parentheses, things like that, that we are currently not able to support, and the indexing of variables with variables that represent tensors with high orders, I mean very high orders. We also want to measure the lifting time of each one of the approaches, and this graph shows the lifting time in seconds for how much time it takes for each approach to produce a solution. We can see that both neural-based approach and MT and ChatGPT, they are stable across the whole switch because they don't involve a search. They just directly output programs. And TF coder, it's surprisingly fast for the programs it can synthesize. Sometimes it's faster even than the neural-based approach, but that speed comes at a cost of coverage as it timeouts for most of the programs. Our ETS, it's more scalable than TF coder, but it still takes a lot of time for most of benchmarks and times out for a bunch of them. And C2 tackle is slower than the neural machine translation based approach, sorry, but it's on average faster than the purest synthesis approach. And this shows that using the code features as a guide during search really helps to decrease the search space and leads the algorithm towards the solution. The main reason we wanted to lift programs to begin with was performance. So we measured the performance of lifted kernels against the original implementation. So on the left we have the speed up we get when we compile those programs down to the tackle-generated CPU versions, and on the right you have the tackle-generated GPU version. And the baseline is the original implementation compiled with GCC -03. On the CPU, our programs are on average 1.79 faster than the original implementation. The high speed up value was 5.33 on the GSP Stone benchmarks, and the lowest speed up was 1.21 on the darknet programs. On the GPU, our programs, we got a speed up of 24.11 times on average, and this shows that, yes, thanks to the tackle optimized code knowledge and the generation mechanism, we are able to get faster programs by translating our programs from the original shape to a more specific language. So in conclusion, we conclude that lifting is a feasible task for the range of applications we found, and the usage of I/O pairs, equivalence behavior, plus code analysis, it's efficient in help search-based synthesis methods. We are to outperform existing techniques and found and achieved a high coverage of 95%. We show that we can get some speed up by doing lifting, on average 1.79 on CPU and 24.11 on the GPU. And for feature work, we aim to also target sparse algebra, so it can handle more benchmarks and improve even further search by maybe using neural-guided synthesis by training a network to help the synthesis, but also using the features from the programs. So yeah, that's all I had to say for you today. Thank you for your attention, and if you have any questions, I'll be happy to answer them. Thank you.
So thank you for your talk.
Thank you.
Do you know about Poly? Yeah. Have you compared it for the CPU with Poly also? Is this something you did during your implementation phase or testing phase?
No, we didn't compare against Poly because we just compared against the, you mean the speed up of programs?
Yes,
right?
yes,
Yeah.
yes.
So we just compared against the original implementation because we wanted to show that if you have the original implementation, we can get to fast programs by just doing this translation. But but no, we didn't compare against Poly.
Okay, so if I said it correctly, it's not to optimize in the low-level sense, but to optimize in this high-level C sense to generate better code and not generate better byte codes.
Yeah, so we are not, let's say, the speed up we get is not made by our synthesis. Like, our synthesis doesn't make programs fast, but our synthesis makes possible to port that programs to platforms that will make them faster.
Thank you.
Thank you.
Thanks for the presentation. I have a question regarding the guarantees. Is there any kind of proof that the generated tensor algebra expression is correct?
So we don't formally guarantee that the program is correct. So like we assure that they're correct under the I/O specifications we generated. There is ongoing work on that because we've tried to use some kind of form verification on the programs, more specifically model checking, but we found out that for the programs we have, that didn't scale. So like for the simple programs, it worked, but for the most complex program, it timed out with like more than 1 hour of running time. So we found that that's not feasible to insert in a loop where you're testing a lot of candidates. But yes, it's something that we wish to add to our pipeline.
So there was one slide where you were kind of showing the design space, like verified lifting and the other approaches. I think it was one of the initial slides. I wanted to understand better the trade-off between each of these approaches, because as far as I understand, verified lifting actually ensures the correctness.
Yeah, it does. Verified lifting, the programs that are translated by verified lifting, they are translated from a summary that's proven correct. However, using verified lifting, we were not able to express tensor algebra in their formulation. So like the kind of computation we are doing, it's, I think it's too complex for the symbolic reason they use. So we tried to use that framework, but we found that the language was not expressible enough to capture the semantics of the tensor algebra programs.
Thanks.
Thank you. I think he has a question.
Did you see someone?
No. I thought you had.
Oh, I always have questions. I don't think I get a chance. So I was curious, I guess, the synthesis you do, can you explain again how you sort of ensure that it matches that the code you generate matches the C code?
So
the same semantics?
yeah, we are checking this by behavior equivalency, which is basically given our candidates, they are well formed, we will run them in the I/O examples that were generated using the original code. So we generate I/O examples with the original code, and then we run the candidates to see if they match.
And how do you sort of ensure you get enough coverage, that you generate enough examples to...
Oh, so like we currently just generated like a lot of examples and run it, and we don't ensure we don't provide any kind of formal guarantee. We just use that I/O examples, but from our experience, it's not something I can't prove, but for linear algebra examples, usually they at least for in our synthesis, the candidates, they either fail in all examples or they pass in all of them. So I think for the nature of linear algebra, the linear algebra we are dealing with, it's, I think as you add more examples, you still will have to reach the same conclusion. So I think you don't need like millions of examples to prove that. But yes, I mean, our coverage is just based on number of IO samples.
You feel you have enough.
Yeah.
As a follow-up to that, so you mentioned that one of your features would be considered sparse tensor algebra.
Yeah.
I think over there the problem is going to become more interesting because for dense tensor algebra you don't have complicated control flows.
Yeah.
But for sparse tensor algebra you could have all these weird kind of things happening.
Yeah. Yeah. We have a challenge with sparse algebras because when you're using Taco and you need to check the program, like write your program Taco, the dimensions of tensors, they need to be explicit. So like, you need to give concrete numbers. And let's say if you need to instantiate a tensor, if it's sparse, you also need to give the coordinates. And we found hard to extract those coordinates from the original code. So like working on sparse algebra also involves some work on that front. But yeah, it's definitely more challenging.
All right, well, let's thank our speaker again. Thanks.
Thank you.
Oh, no, it's a big one. So only if you have just some easy ones. So then I'll stand here. So. Okay. So let's try. Oh, great. Works. Thank you very much. You have been selected, so yeah, it's surprised.
Really? It's like I think it's the most cited paper from 2012. It has quite an
Actually,
impact.
so this is not my main research topic, but actually I saw sometimes you get these mails about you have been cited there and there, and I saw, oh, so people are interested in that paper.
All these mails add up. Well, I'm looking forward to it.
Since I registered here for PPDP and Lobster first, I
okay,
was not
yeah.
even aware of the fact that GPC takes place.
Right.
So,
Yeah.
yes.
But
Good that
I
it worked
really,
out.
yeah, I'm glad that it worked out because we were very last minute with notifying you guys. Apologies for that. We didn't know that last year there was no award given. So,
Okay.
this should have been the.
Why was it last
I
year?
think people forgot simply. The organizers forgot to do so. I realized recently. Okay. It should be fixed. So this year we have two, one for 22 and one for 23. There should be about 20, 25 people. Not that many people. No, I think it's maximum 30 I've seen talks before. So. Sorry.
No, it's fine.
So which university are you working on? It's
Kiel
Kiel
University.
University.
Kiel
Okay,
University. Yeah. So at the end, I will also show you Kiel is.
Okay, nice. Okay.
So all this has been taking place inside Kiel, also with different companies and so on. And basically, I will talk about so the history of this work and so on, and no technical talk. So
Okay,
just
that's
about
really
the-
nice. So it's really about X-text and space and
Yeah,
extend. I've used some of these myself in the past. So.
Oh, yeah.
I think many people here will be.
Very good. Yeah.
So it's nice to get a bit of context.
And what is your main work?
I work in software quality in general, so program transformation, architecture, vulnerability detection, refactoring.
Can I briefly check before you go ahead? Just to make sure that everything.
The second most influential.
Ah, yeah, okay.
Not the second most influential.
Not the second. the actual most the current most influential talk.
Just
So
double
this
checking,
is,
but usually it should work.
others are on the first floor. Like 5 minutes this morning walking around. Yeah, thank you so much. Okay, so thank you very much. So we are very honored to receive this award, and here you see also all the authors of the original paper, and unfortunately only I attending here the SPLASH conference. And yeah, the reason is my working topic is more related to declarative programming, therefore I'm attending PPDP and Lobster here. And the other authors didn't plan this because the first 5 authors are in the industry. Also, here these 2 authors are now freelancer, and I will tell you later about this. What the first 3 are doing now, and yeah, and Willy Hasselbrink and me, we are at the Kiel University, and Willy Hasselbrink is actually has the chair for software engineering or software technology in Kiel. And I have the chair for programming language. And at some time, before we did this work together, so he asked me, might be an interesting topic for joining this. And yeah, it was quite a successful collaboration. And since I must also say that Willy was really the driving force behind this work, as I will tell you more, and therefore he prepared also, designed the talk and prepared the slides for me, so all your gratitude should go to him, and if you do not understand so much, that's my fault, because I'm not such an expert as Willy. So instead of give you technical details about this work, which was already published 11 years ago, I will try to give you some background, what was the road that leads to this work, and maybe this explains also why people seem to appreciate it very much. So at that time, 2012, so the context of this is really earlier. So the context of this work is model-driven software development, and this is the main motivation, all of this. And yeah, and at the time it was, I think it's still, but at the time it was a quite popular approach to develop software. And at the time in 2006 also there was 2 people, they are also from Kiel, I will talk about them later, Thomas Stahl and Markus Völker, wrote a book about model-driven software development, which was quite good appreciated of this. And the basic idea of model-driven software development is you want to develop your software in a more high-level style by specifying a model of your application and then try to generate most of the code from this model. And since there is no unique language for all kinds of applications, you need for different applications area, you need, of course, different languages to express your model. And therefore, domain-specific languages, which are particular languages, formal language for particular application domain, are at the center of model-driven software development. So, and this is also the area where we worked here together. So basically, before I become more specific, also a bit more general, basically there are 2 main approaches when you want to design and implement a domain-specific language or language for a particular application domain. One approach are internal DSLs, so where I have more worked on it. They are also called sometimes embedded DSLs, and the idea is to embed a DSL into a already available host language. And of course you can ask, so what then I can use directly the host language. Of course, this makes only use if the host language is powerful enough so that you can easily provide other abstractions which are useful for this application domain. And therefore, historically, and I think also up to now, often declarative programming languages, in particular functional programming language, have been used for this. So this is a very old idea. It originates from Lisp. And yeah, and from this point of view, a domain-specific language can be considered as a special library, which is a specific API for this application domain, and for the design of this API, to design it, it pushes the host language features to do this. And therefore, it is quite important that the host language allows you to define abstractions in a dense and readable way. And therefore, so from my point of view, often Java is not the right way, because in Java you have so much boilerplate code and so on. So it's not so easy to express. So this is one approach, and I will discuss it further, but the other alternative approach are external domain-specific language. So that means they are completely independent of an existing programming language. So it means you define a new language just from scratch. So with a parser and compiler and so on, type checker and so on. And so that means you need a complete new language implementation. And of course, this has been also done, for instance, the AWK programming language, very old one for file processing, which is specific for file processing, or another language, which I will also show you later a bit more, a language for programming railway control centers, which is called Menges, and this language has been also developed later with the tools which I'm talking about. And of course, as I said, such external DSLs need their own infrastructure, so which you have to implement from scratch. So, some words about internal DSLs. So, as I said before, they are built on top of general programming language, and this is also a slight restriction because the syntax which you can use are constrained to what the host language allows. So that means if I want to write something which is not allowed in a host language, I cannot easily express it. But there is a big advantage, because in order to implement such a thing, basically a DSL is a well-designed library. So that means you have to spend some time in designing it, but you do not need any new language infrastructure. But you can just reuse the parser, compiler, interpreter, and also maybe IDE of the host language. And since you can, and basically at some point, you can also decide to reuse all the concepts which you have available in the host language. For instance, expressions, so that you can, which are often the most complex part of a language, and you can just reuse expressions of the host language. And if you type them, you can also make a write restriction to do them. But on the disadvantage, on the downside, if, as I mentioned before, you have only a limited flexibility, because you can only use concepts which the host language provides. And this is also motivation for this work. You have no specific IDE support for if you deal with them. I come later to an example. So, or in domain-specific compiler checks, so that if you get error messages, you only get the error messages of the host language. I can tell you, so for instance, if you implement a DSL, embedded DSL, for instance, in Haskell, which has a reach type system, if everything works, the description is quite nice. But if you make an error, you get sometimes really big error messages, type error messages, and you are completely lost. So therefore, our interest in relation to this paper are external DSLs. And for external DSLs, the author of the book, Stahl and Völter, had also developed an so-called open architecture-aware code generator, which was exactly the idea of this, or which should solve these problems and make the implementation of external DSLs quite easy. So at least for the implementer of a DSL. And here's basically the structure of the tool, which is not important, but only what is here in this box here. This is part of the open architecture-aware tool. And if you want to implement a new language, you have to specify your input model. You give some additional templates for code generation, and then you can translate the model. You can read the model and translate it at the end. At the end, you get the generated code out of this. And at that time, it was 2006. People were also quite often using also visual specifications, because at that time, UML was quite popular. It's still popular, but at the time, it really started off. So therefore, the idea of this tool was to specify the model in UML notation and then this UML notation, you can export it into a textual representation, and then this textual representation is read by the tool and the code is generated. But I think, so visual tools or visual programming is quite nice if you start off. So therefore, you have also for pupils in school or beginner students also, sometimes they are also developed visual programming language like Scratch and so on, but if you use it and you became more expert, then you want to use more things which are not directly supported. So if you become more experienced, the idea is, so sometimes visual programming is not so good at only graphical notation. And therefore, this was also the motivation for the introduction of Xtext. So Xtext is the main motivation. It should be support writing external DSL, but where you write your specification in textual form. So, and this is a framework for it. That means you specify basically the grammar of your DSL. You just have a context-free grammar for this plus other part. And out of this, you just push a button and then you get from this everything. That means not only a parser, which is just standard, but you got also IDE support. So that means at the end, you have also an IDE available with also specific support for your domain. So this is an example here for a language, domain-specific language, which allows you to specify finite state machines. And here it has been used, for instance, to define a CD player, where you enter a specification, you say, it's a state machine CD player, and then you can define the different states and how states are changed and so on. And this should be just show you, this is highlighted here. If you make a type error, you get here the message, or your typo, not type error, a typo, you get an error message which is related to the domain. You get here the error message that the state of is unknown, and not if you use an internal DSL, you would just get the message of is an unknown identifier. So you get more better error messages related to your domain. And initially it has been implemented with open architecture where, because this was also an open source project, but this has been integrated in the Eclipse project, and it received also in 2010 the Community Award, so this is what seems to be quite well appreciated by the community. So, and another example, this is just a play example, but another example which has been, where Xtext has been really used, also with some people here, which also involved in the paper. It has been called Menges, and the idea of this project was to provide an external DSL for programming railway control centers. And there in railway, in railway control centers, you have on railways, you have different switches, which must be set and changed and so on, and therefore you have high reliability demands and also security demands on these control centers. At the end, these control centers are programmed with a specialized hardware, so programmable logic controllers and so on. And therefore, there was a demand to have a high-level specification for a particular application, and the code generation should be code for such controllers. And this has been also at the time implemented with Xtext, and here you see just one example of such a control system where you can specify, have devices, and you have elements, and then you have switches where you with different identifiers and so on. And here you see you have directly entities related to your application domain. And something about the context. So here also Willy, the co-author which I mentioned, he was also involved in this project. Then also Thomas Stahl, the author of the book, and a colleague of him, they work in the industry. So B&M Informatik AG is a software company in Kiel, which also produces banking software, but also other things. And Funkwerk was a company which was really the partner, the industrial partner for producing these rail system controllers and so on. And then there was also another colleague from Kiel, which is the head of the real-time and embedded systems group. And at that time, within this project, there was an observation, because if you look at this here, if you just use here, you often have really only a simple structure, but you sometimes need, if you want to define more of the logic about the model, you need often also more complex expressions. And this was a motivation for this paper here. And so in principle, if you need more complex expression in your external DSL, of course, expressions have a context-free structure. You can define these expressions with X text. But on the other hand, expressions causes some effort to implement them, because expressions have a recursive structures. You have, for instance, operators where you have different precedences, associativities of the operator. Sometimes you have ambiguities which you want to solve by some rules. Expressions should be typed, should be well typed, and so on. And if you implement this, yeah, it's basically an important part of any compiler for a standard programming language. And that means if you need expressions for your application domain and have to implement it, it is a lot of effort. And therefore, most external DSLs which are implemented with Xtext and also other tools, they focus on structural aspects. So mainly here you specify the structure of your application, but the details here, the detailed logic about this is then, because you do not want to implement expression, then the details are delegated, to another general purpose language. So if you know, you generate, for instance, from this model, you generate code for Java, then you can say, okay, maybe I allow to write just strings in my model, and these are then Java expression, and then they are just compiled into Java. Or you have a particular places, you have particular markers where in the generated code you then type in your expressions, but then you have the problem if you change the model, run the code generation again, then you have a problem. So this approach introduces really complex, or could introduce complex problems which you have to solve, and often there are also sources of errors, and in general they compromise the high-level abstraction which you want to achieve with DSLs. And therefore, due to this observation, we ask the question, is it really necessary for domain-specific language, for each domain-specific language to define your own expressions? And therefore, the answer, of course, was no, because if you implement expression or provide expressions for domain-specific language in a quite general way, then you can just reuse also expressions in your language. So this was the basis of the next project, XBase, and where then I came in here, and Sven Eftinger, though they have worked with his colleagues. So in the company Itemis, they have worked on Xtext, and he had also the ideas, let's try to have general expression. So this was basically the contents of the paper. So this is just the contents, the main topics of the paper, just in one slide. So what is XBase? So XBase, the idea is it's a reusable expression language which is fully integrated in Xtext. So if you want to use Xtext to define your domain-specific language, you can need expression, just reuse XBase. So, and it is a powerful expression language. It's integrated because, therefore, this was a title in our paper. The target is Java, and therefore it is fully integrated with GVM of course, like in Java, it is statically typed, and it also uses type inference, and it's also, in some cases, also, or in some aspects, also adaptable. So, for instance, instead of a fixed set of operators, you can also redefine operator and support operator overloading, which might be resolved by types. So basically, the language XBase is close in the syntax to Java, but it's not Java because there are no statements, they are only just expression. But on the other hand, it offers also more of Java with respect to Java at that time, I must say. So there was also a concept of lambda expression closure, but with a different syntax, which is now available in Java, which came in Java 8. You have powerful switch blocks, and there is also type inference for variable declaration. So that means you just can introduce variable by just an assignment, and from the type of assigned expression, the type can be inferred. So maybe you think, so this is not so, nowadays we have it also in many other languages, but at that time this was also new, at least in the Java area, and maybe we were also with the design of the language ahead of our time, and maybe this was also the reason why people were interested in this. So basically XBase is a generic expression language, so it is not a full programming language. You can consider it as a partial programming language. We are only expressions are relevant, but the important point is embeddable in Xtext. And as I've shown you, with Xtext, you get also an IDE for free, and therefore you can also write your expressions in Xtext that get also the IDE, type error messages, and so auto-completion and all the things also for on the expression level. So you do not have this break in different level when you want to use expressions. So, and it comes also directly with a code generator and an interpreter. So, and therefore one can, just a selling point, you can use XBase if you just want to specify computation. So, or you want to specify something more about the semantics of your model via expression in your DSL. So maybe you want to calculate values if you, for instance, in a finite state machine, if you make some switches and so on, how the new values are, and also if you need complex type, because XBase is also a typed language. And as one application which has been done, I showed you also the industrial application, but one application example I want to mention is Xtend. So this shows you, with this approach, you can also define a standard programming language where you, in a high-level manner, where you get for free all the features like compiler, parser, and IDE for free. So an Xtend is a statically typed functional object-oriented programming language, so maybe quite with its features also similar to Scala, but this has been also developed at the same time. And it inherits all the features from XBase, so the expression language has been used from XBase, but it has been extended by particular expressions, so for instance, multi-line strings and class declarations and so on. And and since this has been implemented with XBase and Xtext, so then you provide at least an integration into Eclipse and also with the usual support. So, just I want to come to an end, and just I've talked a lot about of Kiel, and maybe you do not know where Kiel is. Therefore, here is a short map. So we are here in the Hotel Miragem, and in the very far north of Germany, there is Kiel. So this is almost at the Danish border here. And so, and if you want to go by feet to Kiel, you need 600 hours. So this was calculated by Google Maps. So it's a long trip, but of course there are also flights available, not directly to Kiel, but to Hamburg. Okay, and Why I'm talking about this? Because also inside Kiel there is some geographic had been taken place during the development of the project. So this is basically Kiel, and this is here the Baltic Sea, further called, and B&M Informatik AG. These were the authors of the open architecture, where they are in the west of Kiel. Then Itemis, which is a company which was here in the area for new companies in Kiel, which is not far away from the University of Kiel, and this basically was a cooperation which led to the paper. Now, people, the authors, the main authors from the industrial side, from the paper from Itemis, now moved more to the east of Kiel. They funded a new company, Type Fox, and later they founded also a company, JITPOT. And just in the summary, I would like to mention this, but just to summarize. So Xtext, if you maybe many of you know it, but it's a commercial, so it's also I think there is also trademark from this by Eclipse. So it's an open source software framework for developing textual domain-specific language. And it started originally as an offspring of the open architecture and the main contribution of this paper to add reusable expression to Xtext. And since then, this combination of Xbase and Xtext has been used in professional software development, but also in other technology transfer projects where also always Willy Hassenbrink were involved, like the Mangas project, which are already mentioned here, and also in academic research project, because we are in Kiel, it's the Baltic Sea. There are also many initiatives also related to ocean sciences, and for instance, there have been developed an ocean-specific, domain-specific language, or another language for checking fish populations like the spreads, and these things have been also done with this Xtext Xbase combination. So what is the situation now? So I do not know how many people are now still using Eclipse. Now there are also other tools, and therefore also the authors who have developed at Itemis, these things now moved in a new area where they support IDEs in the web. So for instance, the latest thing where they are involved in is JITPOT, which is in principle things where you can programming your JIT, your software in different language, but where we have support, which is then supported by JIT or GitHub and so on. And therefore, this may be also the things. So I do not know whether this is still used, and because these are also projects, but at least it gave some influence at that time to the development of domain-specific languages. So therefore, thank you very much for your attention and also for considering us for the prize.
Thank you and congratulations. Maybe I'll start with one, just to break the ice. So you mentioned in the beginning this categorization of domain-specific languages into internal and external. Mm-hmm. Are you aware of comparable efforts in the internal DSL world? For instance, where you could specify the grammar of your internal DSL and then have the IDE of the host language adapt?
No, I'm mainly aware only of internal DSLs which are implemented for functional language, and then they just use the IDEs which are available there. And the problem with the expression is not there because they have just the expressions of the underlying host language available. So, and of course, what is sometimes available, so it is so for instance, there are approaches that you can write, for instance, SQL expression and embed directly in the textual notation of SQL expression in a language. And this is often done in a way, so in order to have it in a safe way, so that you allow in a programming language strings from another language, and then these strings are passed by a preprocessor and then replaced by the things. But I'm not aware of approaches where you get immediately also IDE support for these embedded strings.
Yeah.
So,
So maybe that's something for future work.
yeah, might be interesting. Yeah.
Has this triggered a question? Yes.
Yeah. So can you clarify exactly what you mean by the IDE support? So because if it's an internal or embedded DSL, so as I said, so it's basically already has all the IDE support for at least for whatever constructs that language has. And I wanted to mention the line of work on Scala, related to Scala macros, and also Scala Virtualize, which try to kind of extend some of the language features and these things. So perhaps can you elaborate a bit on the?
Yeah, maybe a little bit. So for me, IDE support, the most important thing is that you get also support related to your DSL. So as I mentioned, often you provide so for instance, if you design an internal DSL, you provide new types, for instance, for entities, relationship, make new type definitions, but define the types in terms of other more complex type where you have the internal things available like monads and so on. And then they are often just other names for these internal types. And if you make an error, you just get on the IDE level, or even if you just write something. So for instance, an entity, and often the IDE shows you immediately what is the type of the entity which I'm writing, and often you do only the C then the types of the language. So it's difficult to hide it. So this is what I would consider as better support, that you really get error messages, so in terms of the domain and not in terms of the underlying programming language.
I'll stand up so you can see me in the back. Thanks for your talk. This is very interesting, and I remember this from some time ago. So my question is a bit of a friendly challenge, I guess. So the question I sort of have is how difficult is it to build expressions from scratch? I feel like to some extent we all sort of know how to do this, or at least, and where is the sort of pain point that made XBase and Extend and Xtext so obviously successful? Because I feel like it's something that, well, if you can live with some conflicts in your LR parser and fiddle with precedences, maybe you can get there. And, the Rascal folks would say, well, we have these nice GLL or GLR parsers, and you can fix your ambiguities sort of as bugs. Has that work sort of progressed to the point that you think it is more useful than it was then? Or what is it that sort of made it's such a challenge, why this was so well received that people perceive it that way?
Yeah. So I would say it depends on the kind of expression. So if you just say, for instance, Lisp or Scheme is my programming language, I only want to write Lisp or Scheme expressions, where you always have parentheses around this, so this is easy to I think to pass. So the main problem is if you have expressions where you have infix operator with different precedences. So even if you look, for instance, in the formal description of the grammar, so like in Haskell, where you have 10 precedences, or in Prolog, you have, which is quite more flexible, where you have 1,200 different precedences. So if you really want to, you can write it as a context-free grammar. But what you have to do is you have to parameterize the expressions by the precedence level, so that you say that you, for instance, can say an expression of precedence 10 contains two expressions of precedence 11 and then an infix operator of precedence 10 and so on. So that means if you really want to write it as a context-free grammar, it gets awful with this precedences, because you have so many rules. So what is done in practice, I do not know whether all compiler constructors use it, but I know it a little bit, you just parse these first expressions with all ambiguity. So you just say an expression is just a string with infix operators in between, and then you have a separated phase where you try to resolve the precedent structure of the expressions. So and that means you need something specific which you cannot easily express in a context-free grammars. And I think this is the reason. And also if you have, for instance, expression with binders, so like lambda abstractions, so which you often have not, but if you have binders, you have also to consider variables visible in this area and so on. Therefore, expressions are quite complicated. And for instance, if you look, so for instance, in functional language, in Haskell, where everything is an expression, basically this is the main part of the entire language. So I think the easy part are just the structure, if you write class declarations, attribute, and so on. But the really difficult part are often the expression, and therefore it really makes a lot of effort. Mm-hmm.
More questions? I can inspire some more, maybe. So you've explained that there was a lot of collaboration with industry going on while you were developing XBase and Xtext. And I was wondering, what was really first? Was the industrial problem there first, or was the research prototype there first?
No, basically I must say the practical part has been developed in industry by Itemis, because they have developed Xtext and also worked on XBase. And also due to the real industrial project, there was at that time there was a demand to do it, and maybe I do not know exactly, but maybe Willy Hassenbrink, who was involved there, said, so maybe we should do it better instead of writing expression and delegating everything to the other language. Let's try to integrate it. But everything this from the implementation point of view, this has been implemented by the Itemis people.
Other questions? Yeah, in the back.
Maybe one small question, because we were talking about how to construct those expressions from scratch. How do you deal with different worlds where you want to have different expressions? Can you cut it in some kind of way that you only deal with expressions that you actually want?
Yeah, so I'm not sure about these details, but I know you can, if you want to use XBase, you import the basic framework of XBase, and then you can adapt it to your wishes by doing more. And so I'm not sure whether how you can restrict, for instance, the expression language or use different expression on different parts. So I must say.
Maybe put it the other way around. So you don't currently support multiple modular things you can bind in, but you get the whole expression library, right?
Yeah, exactly.
All right. Maybe as a final question, is there anything you would do differently now, in hindsight?
I would do differently. So so only I think it's basically maybe move away from Eclipse to support just language, the language server protocol to doing this, because I know we also did at that time also try to have an Eclipse plugin for language which we are developing, and after 1 year, so this was a master work by some students, and after 1 year when the new Eclipse release came, we could not use it anymore, and it was so complicated. And I think with this new modular or better defined structure, it is better. And therefore, I think this is also the reason why the people are now moving, for instance, to web-based application using language server protocols. But I think the idea was quite nice.
Yeah, I agree. So thanks again for your talk, and
Thank
congratulations. Our next speaker is Sandro Schulze, who also won an award for the most influential paper, this time from the 2013 edition of the conference, so exactly 10 years ago. And the award is for the paper does the discipline of preprocessor annotations matter? A controlled experiment. And again, the steering committee selected this paper based on the impact it has had and still has, because one of the major deciding factors in the discussion was the fact that there was not just a high number of citations when the paper was published initially, but the paper is still receiving and continuing to receive a lot of citations. So Sandro, congratulations.
Thank you very much. Thank you very much.
And the floor is yours.
Okay, good. So, everything off. Okay, so thank you very much. Yeah, for the warm welcome and for the award, of course. Yeah, you see the title is a little bit different, so it already has a little bit of the reflections that we did after we got to know about this award, right? So this is joint work together with Jörg Liebig, Janet Siegmund, and Sven Apel, which are now at different locations. So Jörg is in industry, Janet is a professor for software engineering in Chemnitz, and Sven is professor of software engineering in University of Saarland, and I'm at the Anhalt University of Applied Sciences. So let's have a look at this gang of four one more time. So these are the four people. That's me and the other three, right? Back then in 2013, it was as followed. Those three have been at the University of Passau. So Jörg was doing his PhD, Janet just started a postdoc, and Sven was a leader of a research group over there, and I've been in Braunschweig. But we all got to know earlier in our academic career, because there's this fun fact that we all have a common origin, and that's basically the University of Magdeburg, where we earlier, 2010 and earlier, I received my PhD there, Sven received it way earlier, also Janet received a PhD there, and Jörg received his master degree there. Okay, so that just as a little information about the authors, and that sometimes everything has a common origin, right? One other thing I want to clarify here, the whole thing, or the whole paper and the experiment we did is in larger domain of software product lines. You may have heard about software product lines. It was once quite popular and maybe still in some areas. However, at some point we also noticed, well, maybe software product line is the wrong term, and so we came up with different terms like highly configurable systems or variable software systems, because there are systems that are configurable, but they don't follow a SPL engineering process, right? I may be a little bit sloppy and use these terms synonymously, so just that you know that I'm always talking about the same thing, right? And in the following talk, actually, I also don't want to bore you with all the details of the things we have done. Though the paper is out since 10 years, right? So actually, there are three parts I want to talk about. The past, so the years before and around the paper, and how it happened to be, and what was the context, why we did it. Then, of course, I will talk a little bit about the experiment we did. And eventually, I will, give our view why, or which kind of impact we may have made with this paper. So we had a little bit of discussion in advance with the other authors, so what would we think, what was the main impact here? And I will talk a little bit about this one in the last part. But first of all, let's go back to 2013. Do you still know what you've done 2013? Or what happened around you in the world? Okay, give you a hint. There are some photos, right? So Steve Ballmer resigned as the CEO of Microsoft. If you're a little bit more in soccer, Frank Ribery was the European Soccer Player of the Year. Snowden, actually the Snowden files were leaked in this year, right? And he had to be fast to get out of the US and get into Russia. Then Barack Obama is sworn in for a second term as the President of the United States. Look, it's just 10 years ago. And so many things are happening right now. I guess there are a couple of people from the Netherlands. So Willem-Alexander is inaugurated as king. Maybe you did not know, now you know. And there was this Euromaidan protests in Ukraine. So, which is also still kind of an everlasting topic, right? There were also some sad news. Some people died. Those three are maybe most famous, at least I picked them up. So Margaret Thatcher, the Iron Lady from the British Empire, died in that year. If you're a bit more in rock music, the second one is Lou Reed from Velvet Underground, great musician, also he died. And the last one, maybe I most likely don't have to introduce, that's Nelson Mandela. Okay, that was 2013, just to get clear which year we are talking about. It seems to be 20 years ago. What also happened in 2013 is that I basically got my PhD, right? So very early in the year, if you see there's snow in the background. And yeah, then started as a postdoctoral researcher in Braunschweig. And also Gypsy took place in Indianapolis, USA, right? So back then, that's very interesting, it was still under the URL program -transformation.org, and it had this very nice, yeah, how to say, icon featured, and it was the first year that Gypsy was renamed. So until 2012, it was generative programming and component engineering, and that was the first year when it was generative programming concept and experience, just to get to know this. And Christian Kestner was the program chair. Maybe some of you know him. Okay, that's just a little bit on the background from an abstract point of view. So now let's get a little bit deeper into a brief history on SPL research around this time. And that is probably, I would say it's likely to be biased because it's my view, mostly, of these times. And the focus here is on how we came to this Gypsy 2013 paper. So it means it's kind of a model view, right? So I leave out many details just to focus on what's interesting or what's important for this talk. Okay, in the very early days, there was a paper called If Stuff Considered Harmful from Henry Spencer and Geoff Collier, which was the first one I know that really, yeah, blamed the C preprocessor and using the C preprocessor, kind of these things. Some years later, independently, at the same year, at the same conference at ECOP, two programming paradigms has been proposed. That's aspect-oriented programming and feature-oriented programming by Gregor Sales and Christian Prehofer. Why I'm going to tell you this? Well, I started my PhD in 2010, and around this time, there was an intense research on SPLs with feature and aspect-oriented programming, right? So you found like features using AspectJ, aspectual feature modules, so we combine both worlds and maybe we get a better thing out of it. There were tools like Feature House for composing things, so a lot of things were going on. It was a little bit like a gold rush, so we have a lot of topics, right? Each direction was kind of promising some gold nuggets. So that was the time and how I felt this. However, I would say around 2008-9, we also realized that, okay, playing around with our feature and aspect-oriented programming toy examples is maybe a little bit too far away from reality. So what then happened was a shift towards what we call annotation-based variability. So where we have mechanisms, annotation mechanisms, that introduce variability directly in the language and not in some specific language constructs like features or aspects, right? This is also reflected by some papers I selected here. There was a paper called Granularity in Product Lines, which is well cited, that discussed the whole thing. Then we have the idea of integrating compositional and annotative approaches, and the idea of why not having a virtual separation of concerns, a second chance for preprocessors. So there are a lot of research around the idea, okay, how do we deal with these preprocessors as a language mechanism for variability, right? And what also happened then, that's why here 2010 is mentioned, is actually, that was my first Gypsy and my first Gypsy paper, and my first conference paper at all, if I can recognize correctly. So it was held in Eindhoven. It's a pretty nice time. And of course, it was about software product lines. I mean, that should not be a surprise now after talking about this for a couple of minutes. Second part, what then happened? So, well, around 2010, there was also more work on this preprocessor and the idea of analyzing real-world systems that use the C preprocessor to introduce these variable parts of code, right? And there are two papers that were kind of a foundation for what we've done eventually. Both of them were by Jörg, one of the co-authors, and one is an analysis of variability in preprocessor-based software product line. So they took these systems and they analyzed, okay, how much variability is in there? How intensive is the C preprocessor used to introduce code that you can just remove by just switching the macro off or something like that, right? And the other one that was even more interesting for us was analyzing the discipline of preprocessor annotations. I will come to what discipline means here in a minute, right? So these two papers were 2010 at ICSI and 2011 at AOSD, which is now programming, right? Somewhat. And they were quite important for us. What also started to happen is that there's more empirical validation of SPL concepts and mechanisms. So far, they were just used and said, well, that's a great idea, let's do it, right? And then people started, okay, what about aspects such as program comprehension? Is that a good idea to use this or that mechanism, right? So we have the idea of background colors, we have the idea of comparing program comprehension between physically and virtually separating concerns. So it started also that there's some kind of empirical foundation. There's also other work, I mean, other studies for instance for verification, but that's a bit out of scope here. So and then eventually we arrived at the year 2013 where we said, okay, I know, just forget. I added one thing on the fly because when I arrived here today we had a brief talk. Well, Sebastian actually asked me why there are so few paper now at Gypsy from software product line people, and maybe I don't have an answer, but what I want to say is that back then, the times I'm talking about, there were a lot of papers from, let's say, the product line community at Gypsy. Actually, I would say Gypsy was, we didn't crash Gypsy, but we had a quite good coverage, I would say, right? I think in some I have 3 or 4 Gypsy papers, so it's at some point diminished. I still don't know why, but just for those of you that are quite new, so there was a quite tight relationship. I mean, for years there was the workshop on feature-oriented software development co-located with Gypsy, all these kind of things, right? Okay, 2013 then, our paper, that already has been mentioned, that, yeah, basically took the ideas from the analysis here part and added the empirical part on top of it. Maybe a little bit of context. I talk about preprocessor variability. What do I mean? This is a very, very simple toy example, right? Let's assume there's a struct, and we can decide whether we want to have a doubly linked or just a linked list. And then there is a macro defined for that, and if it's false, then of course this code is removed in a preprocessing step. So we only have a simple linked list. And if the macro is true, then we have a doubly linked list, right? So that's the idea of using this preprocessor directives, in this case conditional compilation, to introduce some kind of variability on configurability. And yeah, as I said, the 2 papers that were analyzing preprocessor variability were very important input for us. What they have done basically is in the first paper to see how much variability exists in the systems and maybe on which level on granularity. Even more important for us was the second one, and that's how disciplined are preprocessor directives applied, right? We'll show in the next slide what does it mean. And as a consequence, so they were assuming, okay, having this undisciplined preprocessor directives is a bad thing. How to remove undisciplined directives. So that was this paper about. So now what do I mean by disciplined and undisciplined preprocessor directives or annotations? So basically the idea is if you have a disciplined annotation, then it is somehow wrapping whole syntactical units, something that is well-formed, right, and that you also then find in a well-formed way in an AST, like this. Well, this is a whole function, and it is annotated with an if, not if, and then an and if. So either you remove the whole function or the whole function will be in your program, depending whether the macro is true or false. With undisciplined, we mean that this happens on a way more fine-grained level, usually in some kind of non-well-formed syntactical unit, like here. You can do this also on just the parameter of a function, right? And say, okay, depending on whether feature GUI is defined, you use the 1 parameter, otherwise you use just false, right? So in a very fine-grained way. And if you have seen on the previous slide the example, you've also seen you can do this on conditional statements and on all kind of things. So the preprocessor would allow. Whether you want to have it, it's a different story. Okay, and by default, it was considered harmful to do this. And there's a good reason I can understand this. If you look at some code, I recommend Vim for that, then you can find really weird examples where people just cry and say, oh my God, what a mess. So that were at least comments we got in some other kind of experiment. Apart from having alternatives here, right? If, else, or having nested if there's here, these undisciplined directives are considered harmful because they may introduce errors. In this concrete case here, you get an error if glibc and use ISPTS flag are defined. Why is that the case? Well, here we have this undisciplined annotation. It annotates the actual if with the condition and the opening bracket. And here, there's another one that has some statement and the closing bracket. So now if glibc is defined, we will never end up here. But if use ISPTS is defined at the same time, we will end up here. So we have a closing bracket, but we are missing the opening one, right? And the assumption was always, well, that must have something to do with this weird kind of annotation. We don't do this at block level or whatever. We do that at an arbitrary level of granularity, so to speak. Okay, so that have been the assumptions. And there were the conclusion, okay, we need to abandon this undisciplined usage of preprocessor annotations. And again, if you look at this or even more messy code, you would agree, right? However, on the other hand, so far, until 2013, there was no reliable foundation. Right? It was just like, that's obvious. We shouldn't do that, right? And actually, there was no empirical insights on how the preprocessors understood in the one way or the other. So since that has been basically a mismatch, we thought, okay, let's change this. Let's try to put some more evidence in there. And that eventually led to this paper, right? So we wanted to turn assumptions more into a little bit more evidence, right? More evidence than, for instance, when you talk about the Balmer peak here. And we did a controlled experiment, right? Which basically means, controlled experiment, we take people, we put them in rooms, we give them tasks, we let them solve them, and then we check, okay, what can we find out? Here are the details. So there were basically two questions. We were concerned about, okay, do they solve certain tasks correct or not? So what about the correctness? Are there differences if we have disciplined or undisciplined directives? And what about the time? Is there maybe an issue in the time they require to solve these tasks? This is the setup we had. So we had eventually 19 students. They all were in an operating system course, so they had to develop their own operating system, a small one using C. So we could be sure that they had a decent knowledge, not maybe an expert knowledge, but a decent knowledge on the C programming language, right? We built two groups based on programming experience. Here on the right side you see. So we did some kind of questionnaire, programming experience questionnaire. Then we did a weighted sum, and then we ranked this, right? And then we tried to equally distribute participants. We had one problem. There were 3 participants. They didn't show up for the initial programming experience interview, and so they had to do the questionnaire directly before the experiment, and we had to do a coin toss in which group they go. That's why we have this unbalanced groups, just in case you wonder. We had 4 subject systems, namely it was BOA, a web server, DIA, a chart application, some kind of IRC client, and Xterm, which is a terminal emulator. So different domains, that was the idea here, right? And systems where we knew, okay, there is preprocessor used, there are undisciplined preprocessor directives in there, right? We knew this from previous studies. We had a disciplined version, and we did some kind of refactoring to turn undisciplined ones in disciplined ones, right? That, for instance, you can just expand the if-defs, then you have maybe 2 versions of the same function, like the one where we had the different parameters, just with different parameters. So usually, making undisciplined code disciplined comes with redundancy, something that you can observe quite often. We did some pilot study with graduate students and also PhD students to check, okay, are the tasks okay? Is the length of the code snippets okay? So we adjusted some code snippets when the feedback was it's way too long and maybe the time is not enough. We had a controlled programming environment that Jeanette developed back then, so that we could track everything. So we could track scrolling behavior, we could track when they changed something where, all these kind of things. So a lot of log data we could use for reasoning afterwards. And there was a time limit of 90 minutes, which was quite tough. Right? If you've ever done controlled experiments, this is maybe the very upper limit you can have. Now just think of students, how long can they listen to you in a lecture, right? Okay, and then there were different tasks. We had some kind of, we call it mental simulation task, which is like understanding preprocessor annotation impact on program generation, like how many variants are there, which code is included, which lines of code when this is true and this is false, kind of these things, right? Just mentally understanding what's happening. Then we had maintenance or evolution tasks, where they really had to change stuff, right? They really had to do some changes on the code. And then we had last task where we have, it was different, we detecting or fixing errors. So it was different because there was now the same code, so both became the undisciplined code, but one had to fix it, one had to detect the error. We'll come to that. So there's an example for a mental simulation, like for a given configuration here, determine all lines that belong to method check term code, right? And then we gave them a certain configuration, which means stating which macros are true, which are false. For maintenance tasks, it's like extend term resize by a new preprocessor variable for changing the width only, so they need to introduce this in the right place so that this newly introduced macro is wrapping the right lines of code so that just the width is changed. And for detecting fixing the errors, I said it's different. So it's the same code. Beforehand, there was one group getting the undisciplined and the other one the disciplined version. And the task is different, so it's, for one, they had to resolve the error, and the others had to spot it. So what about the results? First of all, we're interested in correctness. See, okay, are there differences? For instance, the assumption would be, based on the assumptions made by previous work, is, okay, there must be a clear difference that those that use the disciplined versions should perform better. That was basically what others suggested. When you look at this, I mean, there are differences, indeed. We also introduced a 3-point scale. We found out at some point, well, they solved it in a very good way, but they did not realize that we have 2 files, not only 1 file. So they solved everything in 1 file and forgot the second file. So kind of these things, that's why we introduced this almost correct. It's a little bit sloppy, I know, but at this point, we found this quite fair. What you see is that in general, there's not a huge difference. There might be here and there a difference, but not very much. So we also performed some statistical tests to see whether there was a significance, and it is not. That means there was no difference in the correctness of solving these tasks between the disciplined and the undisciplined group. What about response time? So that are the box plots for the response times, right? What we can see here, they are close by for each task. It is even the case that the response time for the undisciplined group is lower. That means usually this undisciplined code is a little more compact, and it seems to pay off, at least regarding the response times, compared to have a large redundant code base there when you do certain tasks. There is a large difference, however, for task 7, right? So there's way more time required for the undisciplined group. However, tasks were different here, so it's still a little bit inconclusive. Overall, we can see that, again, there are no significant differences, and there is a slight tendency even that this undisciplined group is faster. We also checked a little bit of our log data, right? So to see, okay, what can we find out here? We found out that most of the participants followed a similar process. That means how they, the way they scrolled the code, time that they spent at certain parts of the code, the changes they made to the code. So it seems to be quite consistent. So otherwise we could say, okay, this is so heterogeneous, there's not very, much in these results that you can report. And there were also people with totally wrong answers, right? Where we are not entirely sure what happened, but we found out that they never used the code search. So they could have used, for instance, for the macros, they didn't do this. So maybe that was the problem, but maybe they also were just kind of, gone. For the maintenance task, we found out that 4 participants had no idea how to solve things, right? Again, I was not really clear why, because they did changes in parts that were absolutely unrelated. If there were mistakes, so like usual programming mistakes or something, they were quite similar, like they introduced the correct variable, the correct macro, but they missed to move some code out there. So there was too much code in this macro, kind of these things. And then we found that 2 participants made syntax errors. That was misplaced bracket, where we would assume, because they were in the undisciplined group, that it was likely because of the undisciplined annotations, so similar to the example I've shown, right? Okay, then there are the research questions to answer, right? In both cases, there are no significant differences, and at all we could say, we couldn't find any evidence that there is a difference. In particular, that the undisciplined usage of C preprocessor is worse for program comprehension than using the disciplined ones. Okay, I'm coming to an end now. That's the last part. What do we think? What's the impact? So we did some statistics. So I did statistics in a word cloud, right? So there are also these numbers, like we have 63 citations. As Kuhn said, it's like quite equally distributed. The highest peak was in 2016. What I found most interesting is when you look at this word cloud and ignore the typical words like preprocessor-based or systems, it seems to be, I mean, it's a word cloud of all the papers that cited us, and then I use the titles, put them in, and that's the word cloud, right? Study and comprehension is quite huge. That means there seem to be a lot of papers that also did some study on this program comprehension thing. There's also some eye tracking, mid-size, right? So, yeah, it seems that we could at least trigger people to do more studies on what's going on with this preprocessor usage. And if I have a closer look at the paper, there are a lot of studies. There are human-related studies and would call it subject-related studies, more case studies on systems. So this is what I found at a first glance, all paper that did studies with humans to get a better idea how the C preprocessor is understood, right? There's one that we did, okay, I'm honest, but all the others are from different people that try to figure out, okay, what's going on there, how should we deal with that, because our results were initial, but still inconclusive, and you can still find out more. And then there are some studies that just did more analysis, like, is there the maintainability affected? Does it influence the occurrence of vulnerabilities? Is there a difference between open source and industrial software systems? All kinds of studies about using this preprocessor-based variability. Oh, and I'm especially proud of this one because here we got the 2017 Gypsy Best Paper Award. So just, yeah, you see, Gypsy played quite a pivotal role in my previous life. So summing this up, what do you think is the impact of this work? I would say, or we would say, that first of all, we put the human back in the loop. Right? So far there was, okay, man, it's preprocessor, it's undisciplined, you shouldn't use it. But there's always a human side when talking about program comprehension, so we put it back in the loop, and others then followed up. In a broader sense, we would say that we did some foundational work to introduce experiments as empirical methods in this line of research. So many others picked this up later on, right? You've seen a couple of papers. So I would say that is another impact that we had when we did this, right? I mean, there have been some studies, but doing this in a controlled experiment with people, that was kind of, I mean, it was not new at all. I mean, we didn't reinvent the wheel. The method was already established in other fields, but in our line of research, that was quite the starting point, and others then just got crazy. Well, and as a third one, I would say we eventually, at this point, refuted the assumption about undisciplined annotations. So that maybe they are not as bad as they are blamed for. Okay, last slide. For you guys, what's the takeaway message for you probably today? I mean, you built great stuff around PLs, right? We've seen a couple of things today, right? Like someone's talking about this architecture description languages. Marcus was talking about this X-text, X-base. However, we should always, I mean, if we do something that is directed towards the end user, the programmer, we should still have in mind that despite ChatGPT, all of this is used by human programmers, right? Code is still written by humans, and I'm pretty sure that will be so the next 10, 20, 30 years. So the question that I would ask you, or that you should ask yourself, do you think about this when you're designing things that programmers are using? And do you take the consequences into account, what may happen or not, regarding program comprehension, regarding maintenance, and so on and so forth? So that's just, I mean, hopefully not too offending. You need to check the reality, right? We need to focus, and that's what we learned here back then, on the human in the loop. And I think that experiments at some point, not always, but at some point are inevitable. And we shouldn't ignore this empirical line when we just go ahead with all these fancy theories and whatever languages we create. Thanks a lot.
We have a question from the room already. That's great. Keep them coming.
Thanks, that's a wonderful talk. So if in the end you sort of come to the conclusion that the disciplined and the undisciplined approaches are not that different, does that mean they're both terrible or they're both good? Because when I certainly have that same first impression of the undisciplined is obviously a nightmare. You should never go down that road. But so yeah, that's my question. I guess.
Yeah, that's a very good question. Thanks a lot. I mean, that's still the. I probably can't answer this entirely. Whether they, the point is, it is used quite heavily. I mean, if you look in Linux, you have more than 10,000 of these options. So there's obviously something that makes this inevitable to be used, right? It's powerful. You can tailor everything you need. Maybe you should ask expert C programmers, not me. I would say I would go with the answer that now I would say they have both, or the undisciplined are less terrible, but wouldn't agree that entirely that the whole thing is a terrible thing. I mean,
if I can follow up, is there a different definition of undisciplined and disciplined that you'd say there are sort of good ways to use this?
Actually, this
syntactic structure is not
yeah.
quite the right.
Yeah. So even when Jörg did this analysis 2010, 2011, he double checked also in some kind of project, and there are usually guidelines how to use it, and the usage that usually is favored is the disciplined one. So you should align with these structures, kind of these things. That is actually what you find in projects. Still, it seems that it happened differently. I mean, when we did a study and we sent out questionnaires to open source developers and got a lot of feedback, and there was like along the line, so in these free text sheets said like, we use it, it's important to use it, but many said we should abandon this undisciplined usage. Again, when they performed some tasks, we couldn't see that there's a huge difference, right? But from a subjective impression, I guess even developers don't want to have these things. I don't know how this happened then in Vim. There you can find really crazy stuff. But coming back to a question, there are indeed guidelines on how to use it, and that is usually more in line with the disciplined ones.
Hi, thank you for the very interesting presentation. Looking at the data from the actual experiment, it seems to me that there's a large proportion of wrong answers. And I actually want to piggyback on the previous question on, did you guys look at all at the, let's say, the cost, both mentally and so on, of actually applying at all these techniques versus something external, for example?
Of course, you always have this in experiments. We try to control, and you can find details in the paper, possible confounding factors that may exist, right? I mean, the first one is that we have equally equipped groups. Still, they have students. I mean, they are not expert programmers, but still, we didn't give them the whole code base. We picked files, In this files, we removed anything that is not related, like too many comments, so that the code is not too long. So we tried that they to keep focus. They didn't know about discipline and undisciplined annotations, but we also did an introductory presentation about preprocessor usage at all. So we tried to somehow control confounding factors as far as you can. They were all sitting in a room. That means, I mean, they couldn't just go up smoking, getting a coffee. I mean, they were yeah, kind of these things. Yeah. Still, of course, yeah. There might be something that we didn't have in mind, but according to the standards that you have for experiments, we were pretty much careful in fulfilling that.
Maybe this one will inspire some more questions. So I'm a big fan of evidence-based software engineering, and we see a trend there into, well, people are starting to replicate previous studies as well to make sure that all variables were controlled for, etc., etc. So have you seen some replication studies of your own experiment already?
Not really replication, but I would say something that was in a similar direction, usually maybe extended, right? So there were there were a lot of things done, especially by colleagues from Brazil. They even then started to experiment with eye tracking and kind of these things. But I would also say that that's maybe now something where I have to blame ourselves. Back in 2013, it was not common to have a replication package.
That was my follow-up question.
And I guess we still have everything, data, and we have the questions, and we have the code snippets. Maybe we should do some kind of posteriori replication package for others. But back then, you know, that were different times, so good that we have the times how they are now. But back then it was like, okay, right? I mean, maybe there was some kind of zip file that you could upload at EasyChair or something like that, right?
Other questions? Yeah.
So, hello. So I want to steal your question from before. If you would do it again, would you look at something different? For example, this almost correct part. Would you implement this, or would you consider this beforehand, or what would you consider if you do it again?
Definitively, we would maybe think in advance how we would maybe deal with this one, or maybe how we can prevent this. It's always the same, right? If you have a very small code snippet, you can control it more. There's not that much, and if you just let them do some single choice answers instead of doing some stuff, but then you get less insights, especially on a for the qualitative analysis. But that would be definitively one thing I would do differently, or we would do differently, that we, with the knowledge, there's something that is almost correct, how do we do it, that we in advance would check. How do we evaluate this, or how do we prevent of this? What could we do? A different one, I mean, there's always what you would like to have is like larger groups of participants, more proficient programmers, but that's usually a different thing if you can't throw with money, right? I mean, that would be another thing that would be quite nice. And maybe today, just to add this up, because Jeanette and also partially Sven are a little bit more now looking really into brains of programmers, maybe we could add this on top. Like with fMRI stuff, really looking what's happening, right?
Yeah. Also, you mentioned the participants. Like I think you had here, it was like around 20.
Yeah, 19 at all. Yeah.
So, would you feel that if someone does this kind of human in the loop study, does adding more participants give you like a better confirmation of your claim, or is it sometimes even better to have like less and then go in on a more qualitative analysis?
It depends on the study. There's one paper I cited on the other that was this love-hate relationship where they did interviews, right? If you do this one, of course, then you're fine with less, but then you can ask more intensive questions, kind of these things. And of course, more is not always better, right? But in such a case, if you have more, at least you can say, okay, we find a similar process for 20 participants, and we find that 100 participants applied to similar process has a different strength, right? But I would even say that more is not better, but maybe different levels of experience would be nice to see how does this differ, right? How does a 5-year, let's say, 5-year experienced software developer differs from maybe a student in the 3rd year or something like that. That could be even more interesting, but that's even harder to do because it's harder to get developers.
Thanks for the great talk. I was wondering whether this kind of study, can it be applied to kind of more modern languages with like more modern support for pre-processing?
For which language you have in mind? Which
I
which
don't know,
mechanism?
let's say Scala with the macro system or Julia.
I think the setup itself can be applied. I mean, you just need to find code that you need to define for your language mechanism and your mechanism what is disciplined and undisciplined, maybe in a similar way like here. The setup can, it can be applied. The point why we applied it here is because, especially in C systems, I mean, you have this wide variety of C systems. They are well matured or not. Yeah, there's a large corpus, and yeah, that's it's just used, right? It's a matter of fact. I don't know how often people use mechanisms in Scala to introduce variability, so I don't know, right? For C systems, that's very clear, right? And you can, I mean, there was this one study of Jörg, find out, okay, up to 15% of the code maybe is variable or something like that. But in general, the whole setup and the experiment could be also transferred to a different language with a different mechanism, that's for sure.
Any other questions? Maybe the final one then. So you mentioned during your talk that when people go from undisciplined annotation usage to disciplined, that often times the code size increases. Is that still a problem nowadays, or is that something that PL researchers can work on?
No, I mean, that's just in the very nature of this disciplined annotations, right? If you take, let's go where it is. If you take, no, wait, this example here, right? If you want to make a disciplined one, that means you make the method call 2 times, one with one parameter or argument and one with the other, right? So that's just like in the nature, and I don't see how this, I mean, there's no abstraction mechanism in C that you could use, so nothing like inheritance or whatever.
So we need better language.
And even then, yeah, kind of these. So that's quite natural that this increases the code size, but still it seems to be, at least according to some guidelines, considered less problematic than having these undisciplined annotations.
All right, so maybe that's something
you very
for
much.
future work, for your next Gypsy paper. Who knows?
Yeah, let's see.
So congratulations again. And,
thank you very much.
Thank you. And this concludes today's session. It's not really a session today. So we'll see you again tomorrow morning at 9 o'clock, if I'm not mistaken, for a tutorial on macro programming in OCaml. So I hope to see you all there.